Okay, and we'll go from current slide, and we will first go over these announcements. I think you've heard them before. You know about the career fair that's coming, the transfer fair days, college transfer fair days coming up in February. Okay, that's the 12th and the 13th. 12th on Birmingham campus, 13th on this campus. And I also told you about the fantastic research opportunity, research for undergraduate at 3 universities, University of Illinois, University of Arkansas, and Howard University this summer for 10 weeks. They pay you big bucks to go. It's a great program, okay? If you want to see more information on that, I've told you about it before, right? Okay. So there's more of those out there. I just don't have any of the information handy about those. Now, before we get started today, there's 2 things to talk about. And one, I can't think of any way around it. If you remember, on Tuesday, I had forgotten to bring my phone in, okay? My phone and my glasses. And my wife, either in the morning when she noticed they were missing or in the afternoon when she got home before I did, she needed to get a phone number off my phone that I had. She didn't. So she went to do that and noticed there was a message. And it was a message from UAB Medicine that they have scheduled me for an eye appointment Tuesday. Okay? It's something like, hey, get over it. Okay. All right. It's sometime around 2:30 or something like that in the afternoon. I tried to find it while I was eating lunch today. She said it was out there. I couldn't find it because she saw it, heard it, and everything. I couldn't find it. I think she may have accidentally deleted it. I don't know. Or I just didn't know where it was. But it was a text message, and I couldn't find it. So I can't tell you exactly the time. I will be here at 1:15, and we will have class as late as we can. And then my appointment is just across the road at UAB West. Okay. What's that? No. Right across the road here. Okay? And as soon as that's over, I'll be back. Now, I don't know if y'all want to stay, because I can't tell you how long it'll take. What's that? Well, it's just a follow-up visit, so I don't think it'll be a lot. But the last time I had a visit over there, they were forever getting to me. So I can't say. So when I come back from the appointment, though, I will pick up wherever I left off before the appointment, and I'll continue. Now, if y'all are here, fantastic. If you're not here, you'll have to just pick it up on YouTube video. But if you can hang around, if you can work on old labs, work on research papers or anything else, and just check periodically to see if I'm back in the classroom, or work on your papers in here, that would be a great use of your time. And then when I do get back, I'll continue with class. Now, if nobody's here, I'll just record it, But if someone's here, you get to listen to it and ask questions and that kind of stuff. Okay. So that's the first bit of bad news. Now, the second thing for people who came in after I mentioned this before, and let me see, I know you just came in, Aisha, right? Okay. Tuesday's class hasn't uploaded yet to Blackboard. So if you're looking for it, it's not there yet. I had a problem with my computer. I didn't know I had it with my computer. A button, somehow it got moved from one position where I always keep it to another position, so it wasn't linking with the internet. So all the courses that I had done since last Tuesday night would upload on my computer, but then couldn't upload to the internet because of that button. I thought something was wrong with the internet, and it sometimes does happen, but it was my bad, and I should have checked that earlier. I checked it last evening, found out that's the problem, so they've been trying to catch up ever since. And it's going to take a while because I had 3 big classes yesterday, plus your class, plus 3 this morning. So they're stacked up in there, and they will upload as we go. Okay, and here, is David. All right. Now, so much for the bad news. Now, David, by the way, before you came in, I was saying Tuesday we're going to start class regular time, 1:15, and then sometime Tuesday afternoon, around 2 or so, I've got to go across the road to UAB West for an eye appointment. They just said it on Tuesday. I didn't know it was coming. It's a follow-up visit from where I had my cataract done last summer, and I thought they had forgotten to schedule. I guess they realized they hadn't scheduled it and called Tuesday and said, you got it. So, I can't tell you exactly what time. It's something like 2:30 or something like that in the afternoon. So we'll start class regular time. As soon as, when I have to go, I'll run across there. I'll get back as soon as I can. If anyone's still here, we'll pick up class where I left off when I left and pick up and have class for the rest of the afternoon. I just can't say how long it's going to be. Sometimes they're not too slow over there. Other times they creep. So I just don't know. All right. Now, where are we now? We're in chapter 16. And we should finish chapter 16 today. And then we'll have the lab for chapter 16. Now, I've already told you this once. I'll reiterate it. The lab for chapter 16 is going to be the first part of what we do in lab will be explaining what your assignment will be for the next couple of weeks, okay? Because this is a lab you're going to have to make observations for a couple of weeks, okay? So the first part of the lab we'll spend telling you how to do those observations. Then the last part of the lab we'll actually do in the lab. And then when we finish that, that will be it. So we'll have class from now until 3:45, and then lab from 3:45 to 5:45. Probably won't take that long, but you see part of the lab you'll be doing at home in the evening or in the morning, whichever you choose to do. What's that?
We gotta go outside, or can we look at the window?
That'll be completely up to you. Outside will probably be a little bit better. Yeah, it's not that cold every night, okay? We had a couple of cold days, but generally it's not too awful bad. Like tonight, the low is, I think, about what it is right up now. So the high of the day would be the low tonight. You know, so it's not going to be so awful bad. But we'll talk about that when it comes lab time. So the odds are we're going to finish 16, so we're going to start 17, and then at 3:45 we'll stop 17, wherever we are there, and do the lab. And the lab may, like I said, not take quite the full 2 hours. That's because you'll be doing parts of the lab later. Now, here's the other thing. Make sure I get all of them in. The test on chapter 16 will be on Tuesday. The last 30 minutes Tuesday. It seemed like the last test popped up, surprise for some people. Since we're going to finish 16, I think we'll finish 16 today, then the lab will be, the test will be on Tuesday. Last 30 minutes. We may get far enough in 17 that we'll finish 17 in the first 2 hours and have a lab on 17. We'll see how that goes. Okay. Oh, wait. Tuesday, I'm sorry. Remember, Tuesday is the day of my appointment. The odds are then we will, if we'll get done as much as we can in 17, then I'll go to the lab. I'll come back and continue in 17. We definitely won't finish 17 or even have the lab for 17. But if anyone's here for those last 30 minutes, you can take your test on 16 then, or you can take it later. Now, leading up to that issue, from what I hear, the books are finally in the bookstore. Do they seem like they have enough? Good stack? Okay. So if you haven't gotten your book already, they're there. whenever you can get ready to take 1, 2, or soon to be all 3 of the tests, get those caught up. Now, one other thing. Monday, I've got office hours 8 to 10 and office hours 3:45 to 6. During one of those office hours, I'm hoping to get on the phone to Samford University to see if they've got anybody in the planetarium yet. The guy who was there got a better job offer up at NASA in Huntsville, a really good job offer. He was a really fired up young man, and he jumped at it and took it. And as of last fall, they hadn't replaced him yet. I don't know if they have by now. So I'll check on that, and if it looks like we can do something, the earliest that will happen would be Thursday, but I will do whatever time he can schedule it. Okay? So we'll find that out. Okay. Guess I'm going to have to keep repeating this as long as people are coming in. But let me mark criteria here. Yes.
You said that you used to go to
Birmingham Southern?
Yeah.
Yeah, they've converted that. In fact, Mr. Davis, Jerome, said they've converted that to something else. It's no longer planetarium. That's what I understood him to say. Okay, and okay. Now, for those who just came in, sorry I have to keep repeating this, but I want you to know. On Tuesday, I found out last Tuesday when I got home, I had left my phone at home, but I got a text message. My wife got the text message off the phone, found out they scheduled me for a eye appointment across the road here on Tuesday. Okay, which means we'll have class at 1:15, but whenever I have to leave to go to the eye appointment, I have to go. Hopefully it won't be too long, and when I come back, I'll continue and have class for the rest of the afternoon. Now, since we'll probably finish chapter 16 today, if anyone's here to take the test, the last 30 minutes on Tuesday will be the test on this, if you want to. If not, I'll just keep teaching. Okay. And then hopefully by Monday, and I'll let you know Tuesday, if there is a chance we're going to go to Samford for the planetarium visit. As of last term, they hadn't hired anybody yet, so without a director there, we can't have a lab there. All right, good deal. Any questions? Anything we've done so far, how we're going to do it, how we're going to proceed? Okay. So, we're on in chapter 16, Earth and Space. 16.3 is place and time. The place part we did last time. Now we're going to do the time part. Okay, and we've already done parts of this as well, but measuring time, the time standards depend on measuring the intervals between evenly spaced periodic events. Most of these are astronomical events. So here's an example. The rotation of the Earth on its axis, that gives you a day. Okay? Revolution of the Earth around the Sun, that gives you a year. Okay? So these two together are the basis for a day. Kind of the basis for a month. We're going to get to where that comes from. We mentioned it last time. Seasons, definitely from there. That's from the tilt of the Earth and the revolution around the Sun. And the time for a year, and that's revolution around the Sun. Now, there are different ways to measure days, months, and years. For day, it's solar day and sidereal day. Solar meaning based on the sun, sidereal meaning based on the stars. Months, you have two other names. Sidereal is one based on stars. The other is synodic, I think, or something like that. Weird name, okay? And then years, also, there's ways to measure that, okay? And you could say sidereal is one, okay? We'll get to those as we get to them. Anyone need this any longer? I've been trying just to talk to let people have time to get it down. lot of the slides and the basis that we've already talked about we'll be seeing again. And you're going to see them again in the later chapter when we're talking about climate. You'll see some of the same type of slides that we are now, but that's several chapters away. So a lot of this does build on itself in many layers. All right, everybody still writing? All right, everybody got it? Okay. So let's talk about daily time. I think we've already pretty much talked about this. Let me, yeah, I'll do the 8. Now, Earth-Sun motion. If you view from above, you're looking down at basically our North Pole here. The Earth revolves counterclockwise, okay, like this, okay, viewed from above, counterclockwise, around the sun. So looking down at our North Pole, we're moving in this direction around the sun, and rotates in the same direction, okay? We know that. Most of the planets do that. Can anyone think of 2 exceptions of planets that don't do that? Yes. Venus rotates backwards very slowly, okay? Incredibly slowly. And the other, Uranus, it sort of does like this. So it's sort of hard to say which way it's going, but it's sort of going backwards too. Again, a bit more slowly. Not as slow as Venus. Okay, we're not worried about those. We're only looking at Earth's moon system now. On Earth, the sun rises in the east, and that's why it does, partially you're going to do the sun forces out. Okay, and as you see, you'll see Birmingham come up right about here, and then it reaches noontime, and then it sets. Okay, so it's turning like that. Sun rises in the east, sets in the west. Of course, it's not turning. We're the ones spinning. Okay. Now, here's the issue, though. Does one day involve one spin of the Earth? It does if we're referring to the stars as our basis. We're not. We're referring to the sun as our basis. And since we're turning like this, but also slowly moving like this, we have to turn a little bit further to be facing the sun again. Okay? And that's what we talked about in the last lab, and here we're having it in this chapter. Okay? Right here we are on Earth, and at that point right there was our noon that day. We spin one time, and one time we're going to be up here, but we're not quite facing the sun again until we spin. Okay, this is looking down at the North Pole. So we're spinning this way, and when this place is right over the sun is right here. One spin later, this place is right here again. You have to turn a little bit further to get our local apparent moon with the sun. So therefore, our spinning around our axis is shorter than one day because you have to spin a little bit beyond the axis to get, beyond that point to get the local moon that day. That's what while there's 2, you might say, types of days. Sidereal day would be one spin of the axis. Solar day would be a little bit more than one spin of the axis. Okay? So here's what we're talking about. Noon is the time at which the sun is on our celestial meridian. Okay? That's far out from the way. Okay. Our celestial meridian, remember, is from due north directly overhead at our zenith to due south. That's our local meridian, our celestial meridian. Now, when we look back and see the sun cross that, that's when we say it's in transit. When it transits our local meridian, that's our noon, that day. Okay? What we're going to do is go a little bit this way as we spin, and when we're at the same point here, the sun is lagging a little bit because we've moved a little farther, but then by the next day, that's the solar day. Okay? So, the time at which the sun crosses the local meridian, that's the noon. The apparent local noon is at a particular longitude, wherever we happen to be on our meridian, and the apparent local solar time is given by the position of the sun in the sky. That can be measured with now if you remember in the last lab, we used do you remember what that figure 8 was called? Okay, it was called an analemma. Analemma. And they said in parentheses that was, I think, Latin for sundial. Okay? But if we use what commonly is known as a sundial, another name for that is gnomon. Okay? I hope I'm pronouncing it right. Gnomon. Okay? Sundial. 3 names. Okay? Well, 2 names for sundial. One is the figure 8 sundial, that's analemma. The other one that just gives you the shadow of the sun, that's a gnomon. Okay? That's not the time shown on clocks most of the time. Okay? Certainly at night there is no shadow, so you can't tell the time with the sundial at night because the sun's not up. So the mean solar time, okay, here's the other issue. If you remember, when is the Earth closest to the sun? What month? January. Okay? And when it's closer to the sun, it's moving faster. When it's farthest from the sun, which is July, it's moving more slowly. So your day lengths aren't quite the same. Okay? The spin is about the same, but the days are not. So you also have to average the time between these local apparent noons, and that average over a year, that gives you your average day. So here's the 2 effects. One is the Earth's orbital speed changes throughout this elliptical orbit. When you're further from the sun, you're moving more slowly. Closer to the sun, you're moving a bit more fast. The other issue is the equator is inclined to the ecliptic. Of course it is. So how does that affect it? It's not real clear what they're talking about here. But if you think about it, the figure 8 in the lower half is thicker and then the upper half is thinner. So that probably has a little to do with it, but they're not very clear of how that really affects it. So the mean solar day, and this mean does not mean you're treating it badly, that's average. Average solar day is a 24-hour average from the mean solar time. From local noon to local noon, 365 to 6 days a year, then you finally, the average of that is your 24-hour day. That's mean solar day. Is, yeah, right at 24 hours. That's why we use a 24-hour day. Okay. Is everybody got this one now? I know I talked about it a long time. I was still writing. Okay. Yeah.
Can we access the PowerPoint without logging into?
Oh, yeah.
Okay.
The PowerPoints are on Blackboard.
On Blackboard. So
Yeah.
even though
Now they're in a folder.
Okay.
And you have to hit that little arrow. It's either up arrow or down arrow. Which one? One of them opens the folder, one closes the folder. When you click on that, then they'll all open up in there. Now they're by chapter, okay? So chapter 14 had a set of PowerPoints. Chapter 15 did. Chapter 16 does. And every chapter will have its own PowerPoint. So yeah, you can access those anytime. In YouTube videos, you don't just see the videos, you hear me talk about them too. And they stay up there longer. The PowerPoints. Okay. Everybody finished now or some still writing? Finished? Okay. Now, what's a day? Okay. The length of time for the Earth to rotate once on its axis. That's a sidereal day. When you see the term sidereal, that means according to the stars. Sidereal according to the stars. If you see solar, that's according to our star, the sun. The reason there's a difference, we're not going around any old star, it's just our star, so the other stars are sort of fixed in place. So the sidereal day is the interval between two consecutive crossings of the celestial meridian by any other star rather than the sun. Okay? Little variation because of the Earth's constant rotational rate, that's going to be pretty much fixed. Now here's what they got wrong. Or not wrong, just out of order. This line down here should be over here. The sidereal day is 23 hours, 56 minutes, and 4 seconds. And if you remember in the last lab, one of the first questions was, how long does it take to move from one position to another? It was about 4 minutes. Just under 4 minutes. 3 minutes and 56 seconds. Okay, that's how close to 4 minutes it was. So the solar day, because we have to spend just a little bit further to account for the distance we traveled around the sun in that day, that's what gives us a little bit longer solar day. So the solar day is the interval between two consecutive crossings of the celestial meridian by the sun, not by any old star. Okay. The reason is we are also moving around the sun, so we have to spend just 4 minutes longer to get back to a noonal by the sun. Sidereal day, that's just based on our axis rotation. This is our axis rotation. Add just about 4 minutes to it, and you got the 24-hour day. Okay. Now, as they said before, the revolution around the sun changes the Earth-Sun orientation every day, and because we're going different speeds around the sun, that accounts for variation in those 24-hour days. 24 hours is based on the average of all those days across the year. And as you notice, on that analemma, it makes a complete loop, and a complete loop. So it always comes back to the same place. Wherever you start, it's going to come back there. So whatever average you do, as long as you get the 365 or 6 days average, come out being 24 hours a day. All right. Anyone still writing? Everybody got it? All right. Oh, I'm sorry. Again, if you're doing this last bullet here should be over here on this side. That's a sidereal day. This is a solar day. 4 minutes longer than the sidereal day. I don't know why the guy got up. Whoever did the slides got them out of order. All right, everybody finished? All right. Now, as if we didn't have enough names for everything, the equation of time traces yearly variations between the apparent local time and the mean solar time. Now, there are variations here because of the speed of the Earth around the sun. There's other things we've talked about. Now, if we had chosen to do this, we could. Not this class, but several classes in a row. Okay? Somewhere out there is due south. I'm guessing it's right about here. And if we had covered the windows almost totally, except leave just a little hole, just the right location, so that and then we could mark when the sun crosses our local meridian. Okay, all these things we're doing. And then on that local day, on that day, right when it crosses our meridian, that's our actual noon. If the sun were shining bright enough, we would be able to mark on the floor where the sun shone through that little hole in the plastic. Okay, plastic. If we did that and did it for a full year, we would track that figure 8, that analytic. We would do it exactly because that would show where we were good. That's how they got it. That's how they do this. That's the figure 8 that would be on the floor then. The two effects, the axis tilt, that's what gave us declination of the sun, 23.5 north, 23.5 south, okay? And also the orbital speed, that's the east-west deviation. Remember the figure 8 was fatter on the bottom side, thinner on the top side. That's because of the speed, relative speed that we were going. Now, put all that together, that's your equation of time, the cumulative clock. Now, this chapter, in the lab, it called it, same word as a sundial. In this chapter, it calls it the equation of time. And that is, by the way, forgot this one. Figure 1619 in your book is what we usually think of a sundial. That's the one they call a gnomon. Okay? The analemma, which also means sundial, that's what we call the equation of time. Okay? And this is a little ahead of time, but of where we are. Table 16.1, which is on that same page, is talking about the days of the week and their observable heavenly bodies. Okay? Now, the first day is Sunday. That's the day of the sun. So we call it Sunday. That's where we got its name. Most of the other languages, which are based on Romance languages, which means the Roman languages, you'll see it starts with D-O-M or D-I-M, which I take it has something to do with either sun or God. I don't know which. Usually you see both of those with that. The next day, Monday, is Moon's Day. That's where it got its name. And of course, we're the only language, because we're Germanic, that we have M-O-N in it. All the rest I have L-U-N for lunar, or L-U-E or something like that. So that's the Moon's Day. Tuesday is Mars Day. How do you get Mars out of 2? Okay. Well, in some languages, the equivalent god Mars was. Say again. Something like that. It started with T. Okay, but all the rest of them start with M-A-R. Marty. What's the most famous Marty in the calendar? Mardi Gras. What does that mean? Fat Tuesday, because that's the day before Ash Wednesday, when sometimes people go on fast or things like this. So on the Tuesday before that, they eat up like crazy and do Fat Tuesday. So that's Marty, okay, named after Mars. Wednesday, and again, I think the Germanic deity that was considered most like Mercury was Woden, okay, and that's where Wednesday comes from. But all the Romance languages have something that's closer to Mercury. One of them is Myrku something, but all the others have MER somewhere in it. Then Thursday, believe it or not, I always thought it was Thor's Day, Thor being the one of the Scandinavian gods. Say again?
I think like the god or something.
Yeah, exactly. I guess in the Roman thing, that would be most akin to Jupiter. So a lot of the other languages have JEU or JOV or something like that in it. Some of them are quite different. Okay. Next was Friday. I don't know how we get everybody else or most of the others use VEN for Venus. That's Venus's day. Friday. And we use one of the goddesses was Freya, and I guess that's maybe Greek for the Latin Venus. I don't know. And then just what everybody has, Saturday is Saturn's day. Saturn was the god of the sea or underworld or something like that. Huh? Let's see. No, Neptune was the sea. So I think Saturn was it the underworld? I don't know. I never followed those things much anyway. But just about every Saturday starts with SA. Okay, all of them of the Romance languages, and many of them. We're the only one SAT. The others are SABs mostly. But anyway, that's named after Saturn. Why they stuck that in here on this page, I don't know, but since it was there, I thought I'd mention it. Okay. Now, the book gives these examples, and it seems like they're just making up an excuse to give an example. For instance, they say, how many sidereal days are in a year? Okay? Well, it's going to be a little bit more than solar days. Approximately one more sidereal day than a solar day. And they work it out, and they have about 366.243 sidereal days, whereas the solar days is 365.2 something another. So it's just one day different, because we do one more spin around our axis going around the sun, because we spin one more time, so it's one day long, one sidereal day long. Then they ask the silly question, what is the age of a 21-year-old person in mean solar days? Well, you have to multiply 20 years by 365 and a quarter, okay, days, and that gives you how many solar days he had, okay? I don't even see their answer here. It's somewhere here, I'm sure. There it is. No? Mean solar days, 360, okay. Mean solar days, 7,305, okay? So how many sidereal days has he lived? Well, that would be about one more day for every year, so about 20 days longer. And why they take you through all that math, there's nothing to be learned there that I see except just interesting things. Okay? Then it asks how many sidereal days in one sidereal year. Well, they haven't identified a sidereal year yet, but it's a little bit longer. Okay? So we won't even mess with that one yet. Okay. Again, these examples, they sort of like they just threw them in there just to have something to do. Now, for the life of me, I've been trying to figure out why they showed this. I can't quite read that. Some sort of sun's path. Okay? The sun's path over the earth, and it's a rather weird way they've done this. Basically, the sun goes from directly over the equator in vernal equinox up to the Tropic of Cancer in summer solstice, back down to the equator in autumnal equinox, and back down to the Tropic of Capricorn in the winter solstice. Now, they don't quite have the globe right. You see they're showing a little bit here that they also show over there. This point and this point are the same point. They just give it a little bit more of it. Now that has nothing to do with the figure 8. I've tried like crazy to figure out some reason they put this on the same thing here. It's just not. That's just, that basically is a way to look at the ecliptic of the sun, but it's hard to do it on the surface of a globe. Okay, but that's there. The figure's in your book. Okay, you'll see it there on page 418. Okay, when you get your book. This one, however, you can't. If you were to take this point right here, fold the paper in two at that point, you are going to make that figure 8. You remember it's fat down here, and you fold this in two. That makes pretty much your analemma. Okay? This is the clock behind, as shown on by the sundial. That sundial is the analemma, okay, as opposed to the sundial, which is the gnomon. This is the sundial we call the equation of time, too. So there's several sundials. This one is, if you folded this in two, you basically get your figure 8. Okay? Same slide here with just a couple figures with it. Okay. Everybody got it? Okay. Now, okay. There's a blurb at the top of page 419 I just want to mention, and that is saving time. For instance, daylight savings time. Do you save any time? Not really. You got 24 hours a day, every day. When you spring ahead, you lose an hour sleep, but when you fall behind, you gain it back. Except, I never do, okay? In the spring, when I'm used to waking up at one time and going to bed at the next time, even though the clocks change, I still want to, but I have to get up earlier, okay? So I can't fall asleep until the time I usually did, but then I have to get up earlier. Until next year when I'm retired, I don't have to, okay? And then in the fall, do you gain that hour back? Not really, because you usually find some reason to stay up until then, because if you go to bed early, you're probably going to wake up early, and then you just lie there. Yeah, so it never seems to work. Now they say here, at least I saw it, oh yeah, here, it says, Americans who like daylight saving time say it gives them more light in the evenings and it saves energy. Okay? I agree that it gives you more light in the evening. Okay? Well, the only people I can think that really benefit from this are those CEOs that like to get off early and go golfing. Okay? So I don't think that's a very good thing. Now they say in here, farmers complain that plants and animals are regulated by the sun, not by the clock. Now, I've heard many people say, oh, we have daylight saving time for agriculture. No, we don't. Okay? We had neighbors who were dairymen. And whereas the cows wanted to be milked at, let's say, 6 o'clock in the morning, they needed to be milked then. When daylight saving time, they still needed to be milked at that same time, but now it's 5 o'clock in the morning. So those poor dairymen had to get up an hour earlier. They couldn't say, oh, it's daylight saving time, I'm saving an hour. No, you're not. The cows needed to be milked at the same time, not at the same clock time. So anyway, you can read that if you want, okay? So, before we move on to that, let's go to standard time zones. Now, basically what we've done here, if you think about this, okay? You think about it, okay? Sun, you're shining right. All right. right now you happen to be on what later we're going to talk about, the international date. Okay, that's directly overhead. Of course, over here in Greenwich, England, it's midnight. You're noon here, midnight here at the same time. So therefore, all the way around the globe, there's different times. Okay? And if you take the 360 degrees, that is one trip around the globe, divide that by 24 hours, you want to remember what you get? 360 divided by 24, 360 degrees divided by 24 hours is 15 degrees per hour. So every 15 degrees here, like from 150 to 165, that's an hour. There's an hour. There's an hour. Trouble is they don't base like that. They base centered on this. So there's your hour, there's your hour, there's your hour. Okay? So every approximately 15 degrees longitude, you're going to gain or lose an hour. Okay? So the 360 degrees of longitude is divided into 24 15-degree zones. Now, that's adjusted for what they call local consistency. Okay? Now, what in the world does that mean? Well, here's a picture that sort of illustrates. If you came down the 15 degrees on the nose, part of Maine would be on what they call Atlantic time zone, the rest of it would be on Eastern time zone. Well, Maine doesn't want to be in two time zones, so they jig this one over here to include all of Maine on the same time zone. Okay. Now down here in Florida, because their panhandle is so far over here, and they do a lot of business with Alabama, they do let theirs run over. This is Central Time Zone here, Pensacola, a lot of the beaches and stuff like this, they're on Central Time Zone. We're back here in Tampa and Orlando and stuff, they're on Eastern Time Zone. So Florida did split. Tennessee, pretty much the same way. The part over here does more business probably with Georgia, North Carolina, and South Carolina. So they are on Eastern Time Zone here, but on Central back here, because they do more interactions here. Okay. Kentucky also got split down the middle. Not quite down the middle, but sort of. Their eastern cities deal with these cities here. The western cities go this way. Indiana, can't think why, but the bottom part of Indiana is on Central. The rest, most of the rest of Indiana is this way, but because of big old city Chicago here, this northern part of Indiana, they go with Central, because Chicago's on Central. Michigan's almost totally on Eastern, except for that part that's closest to Chicago here. And I think Detroit, Michigan, is also maybe over here. I don't remember for sure. I think it is. But Michigan, remember, has that panhandle up here. They wanted to keep it with the rest of Michigan, even though it should be over here. So they jigged it this way. So even though they're attached to Wisconsin, when you drive down the road here, you go from Central to Eastern time. So it's adjusted for local consistency. Okay? Now, it beats me why they did this here. Okay? It would seem like this meridian here would be the natural dividing line, except for what we just talked about. Half of North Dakota is going to go to Minnesota for their business, because there's not many people living in it. The other half is coming to Montana. So they sort of split it down the same with South Dakota. Here, I don't know what is over here to do. Nebraska, same thing. This part of Nebraska, they look to the east, and this part they look to Denver, into the west. Kansas, kind of the same way. You can tell the areas of Kansas. This is very remote and rural out here. These folks come this way, the rest of them go that way. Texas even, lots of population centers there, but there's Santa Fe, New Mexico, that this part of Texas will go here rather than back that way. So they adjust it for local consistency. Idaho chops off the top and goes to Washington, and the bottom, they go the other direction. Okay? In fact, some of Oregon goes with Idaho then. And the rest of them are pretty much fixed. Now, this is the U.S. 4 time zones, 4 major time zones. Hawaii's out here on its own, and Alaska's up here. Alaska's a big state. I don't know if they're all on the same time zone or not. I don't know if it's the same one as Hawaii. I think it is. Yeah, it looks like it would be the same as Hawaii. I think that may be, I don't remember what they call it. Yeah.
And then Hawaii has Hawaii time.
It's not the same as Alaska. Oh, really?
Alaska has an hour behind.
Oh, really?
Ahead.
They have it. Okay. All right. So that's how they do that. Now, some other countries do other things. For instance, India. We have friends from India, so I happen to know this. They're right centered on 75 degrees here. That would be all of eastern India, but not all of western India. I'm sorry, I said it back. All of western India, but not all of eastern India. But to keep it all the same, they put the whole nation on that. Okay? Now, strangely enough, if I'm not mistaken, they split the difference and go a half hour. So it may be 12 o'clock somewhere and it's 11:30 in India, yeah, or something. At least they used to. I don't know if they still do that or not. Russia, I think, has at least 6 time zones. Okay? They may have more, but that's such a big country here. And of course, the degrees are much closer to each other here too, because it's on the small part of the globe. China must have about as many as the U.S. Several other countries do a variety of things. Australia, I don't know if they go all on one time zone or if they split into 3. Now, I have been in Australia, but I never bothered to. I never crossed the time zone there, so I don't know if they have time zones or not. There, I know they're in the region. But that's what we mean, adjusted for local consistency. Now, like I just said, daylight saving time, you set the clocks ahead in the spring ahead, and fall back. Okay? Set them ahead in the spring, you set them back in the fall. 1 extra hour of sunlight during summer evenings. You don't have any extra sunlight, but you just have longer evenings. Now, if you have to adjust for hours of the day going around the globe, you run into a big problem somewhere. And that big problem is the international daytime. Because if it's 12 in the morning here, it's 12 the previous day here. Okay? So there you change the day. And that's right, almost smack down in the middle of the Pacific Ocean, but not quite. Again, they adjust for local consistency. New Zealand is mostly on that side, except some of these islands out here also belong to New Zealand, so they move the international dateline around here to accommodate them. And again, the Samoan Islands, they try to keep most of them together, or that's Melanesia there. So there is some twisting. Also up here, the Aleutian Islands are part of Alaska, but they cross the international dateline. The international dateline jigs over there to catch all the Aleutian Islands, and then has a jig back this way to catch all of Siberia, because part of Siberia is on the other side of the international dateline, or what would be, so they just adjust the international dateline to accommodate this country. Okay? There's a trivia question if you ever run into it. What's the farthest east in the U.S.? Furthest east you can be in the U.S. What state? Second? You would think. Except that technically, this part of Alaska is in the east. Okay? further east than Maine is because it's there. We moved to the international date line. What's the furthest north? Also Alaska, and the furthest west. Also Alaska, because it's right there on it, okay? And further south, not Alaska, that's why. You're absolutely right. Okay, trivial question, okay. A weird one. Let me make sure I've got Antonio right? Yeah. Whoops, there you go. Now, still missing several, but hopefully they'll be coming in. All right. Technically, the international dateline is the 180-degree meridian. It's designated to correlate days with a 24-hour time zone. However, for practical purposes, they do some modifying. Now, here is a dumb story that I don't know if it's absolutely true, but it was a naval story. Supposedly, somewhere in the Pacific, there is an island, and there's several that could be, that sits smack down on the international dateline. And supposedly, some entrepreneurial bar owner built his bar so it crossed the international dateline. Okay? Built it right across the international dateline. The reason he did it, supposedly, is that when it turned 12 o'clock on Saturday night, and the bar was supposed to close, on the other side, it was just 12 o'clock Saturday morning. So he would just shut one side down and move to the other side and keep his bar open all week. Okay? Now that sounds like something that would have happened in the Navy, but I don't know for sure that it did. But that would be the folklore anyway. That there was somewhere that bar that built right over the international dateline. So on one side it could be Sunday, and the other side Monday, and then also one side Saturday and the other side Sunday. So just flipping sides of the bar. Don't know if that actually happened. But that's the international dateline. Exactly opposite the prime meridian. Prime meridian at 0 degrees and the international dateline at 100. This is what we just talked about. To include all of Siberia on the same day, they jig it over this way, but to include all the Aleutian Islands, they jig it back this way. And then to include all the islands in this archipelago, you might say, they jigged out this way, and all of New Zealand's islands, they went over here. So they moved it a little bit, but technically the international dateline is 180 meridians, with a few adjustments for local consistency, right here. All right, any questions on that? Standard time zones. So let's now go to yearly time, okay? Now, why they have different names for these, I don't know. You have a solar day and a sidereal day. Well, in years, you have a sidereal year, but the other one is a tropical year. Why tropical? I don't know it, but they use it. The tropical year is the interval between 2 consecutive spring equinoxes. That would be like our solar day. This is based on us. And that is 365.24220 mean solar days. Guess what? The Earth is not a perfect clock. It doesn't spin exactly 365 times in 1 year. It spins a little bit more. What is this close to? What fraction is 0.24 close to? What's 24 cents close to? Second, 25, which is a quarter of a day, right? But not quite a quarter of a day. Close, but not quite. So, every 4 years, since you add an extra nearly quarter of a day every year, every 4 years we have a leap year, which we do what? Add one more day to the calendar. Guess what year we're doing that? This year. This is a leap year. Any year that is divisible by 4, and 20 is divisible by 4, we're a leap year. Yes. may have had a cousin too. I don't remember. On my mother's side, I had so many cousins I couldn't keep up with them. But anyway, now, but that's not quite a quarter, is it? It's just a little less than a quarter. So therefore, now think about this. Every century would be a leap year, right? Because 0, 0 is divisible by 4. But to account for this fact that it's a little less than a quarter, on the centuries that are divisible by 4, for instance, the last turn of century we had, 2000, most of you were alive then, right? No, some of you weren't. Okay, but those who were, that year we did not have a leap day. February 28th was the last day of February on that one. Because you have to make up. Every 400 years, they don't have a leap year to make up for that little bit of time there. Now, sometime or another, we may have to do another little adjustment. I don't know if we're going to or not. But anyway, that's how we do. The fact that that's not exactly a quarter. It's close to a quarter, so every 4 years we add a day, but then every 4 centuries, we don't add that day. Okay, 1 day we don't, 1 year we don't. Okay, that's a tropical year, based on 2 consecutive spring equinoxes. A sidereal year is based on the stars. Sidereal means stars. It's the interval between 2 consecutive alignments of the Earth and Sun relative to stars. Okay? So it's about 20 minutes longer than the tropical year. So tropical year, about a quarter of a day would be close to 6 hours short. This is 20 minutes. Okay, so it's not much. Very, very little difference between a sidereal year and a tropical year. 20 minutes longer, that's all. Now, we do make adjustments to keep the calendar year current with the seasons, and that would be the leap year every 4 years. I've never heard of a leap second before this slide right here, so I'm not going to even think about what they mean by leap seconds. Okay? They do have sort of some interesting examples here. How many time zones is Honolulu, Hawaii? And they give the latitude. Who cares? But the longitude is what matters. And Honolulu, Hawaii is at 158 west. And New York City, which is, who cares about latitude, 74 degrees west. Okay? Subtract that, and you get 84 degrees. Okay? Divide that by 15 degrees, and how many time zones is that? Yeah, 84 divided by 15. Second? You get, did you say 5.6? Is that what you said? Round that up and make it 6. Approximately 6 time zones different. Okay? New York City to Los Angeles is 3 time zones different, so it's almost another 3 time zones to that. Okay? How about Denver, Colorado? Again, don't worry about the latitude. That doesn't affect it any. 105 west. And the Bay of Fundy in Nova Scotia, which is 66 degrees west. Okay, that's up in northeastern Canada. Subtract that one and you get 39 degrees, right? Okay, divide that by 15 and you get what? Just a little over 2, right? What you get? 39 divided by 15? Anyone got a calculator? Second? 2.6. So round that to 3. 3 time zones different. So the Bay of Fundy is in what they call Atlantic time zone, I think. And Denver, Colorado is in Mountain. So that's how you account for it. So those were sort of okay. A lot of them are really strange. Okay. Should have done that back when we were doing time zones. I missed that one. So now we've done yearly time. Let's move to monthly time. And I think I've already asked this question. What word do you always see in month? Moon. The years, the days, solar, okay, or sidereal. But month is based on the moon, okay? Or you could base it on the stars, okay? So sidereal you have again based on the stars. But here's the deal with the monthly time. We'll start with the sidereal month, okay? It's the orbital time measured with respect to the stars. So if this was right here, the star that's out here, that would be from this one to that one, that would be one sidereal month, okay? But that's really short because the moon is going around the Earth. So to get full moon, see this isn't full moon yet, you have to move up a little bit further. So the sidereal month is 27 and a third day. No one uses that, okay? The synodic, where that word comes from, so you have solar day, tropical year, synodic month, okay? The synodic month is a time interval between 2 consecutive phases of the moon, so that would be a full moon here to a full moon there, okay? And again, because the moon's going around the Earth, with the Earth going around the sun, in order to get a full moon, the moon has to go a little bit further to get a new full moon, okay? That's about 29 and a half days. It includes the effects of the Earth revolving around the sun and the moon going around the Earth. So it's a little bit longer, not a little more than 2 days longer than a sidereal month. Sidereal months really don't make that much sense. Okay. But because it's such an odd thing, 29 and a half days, you would think that all our months would be either 29 or 30 days. But they're not. What are they? They're mostly 30 and 31, except for one real short month, February again, 28. Now, who came up with that? I'm not sure. Okay? But it doesn't make that much sense. Now, how do you remember which days have 30 and which have 31 days? Say again? On your knuckles. That's how I've learned. But back when I was young, it was 30 days. That's September, April, June, and November. All the rest are 31 except for 10. That's how I remember it. Why didn't someone tell me the knuckle? January, big knuckle. So that's going to be a long one, 31. February, short one, happens to be 28 or 29. March, 31. April, 30. May, 31. June, 30. July, 31. Then start over on the knuckle. August, 31. So only 2 consecutive, well, not the only 2. August and July and August both have 31. So start again with August 31, September 30, October 31, November 30, December 31. But then remember, January was 31. So there's actually 2 sets of months that are both 31. None of the 30s are consecutive. Of course, the 28, 29 of the year. Okay. So.
Wait. You say 28 and 29. Those are from February.
February, yeah. Only one short month like that, and that's February. Okay. So you know how to do it. Your knuckles. Okay. So we started talking about the moon, 16.4, that's the topic. the moon. Now, the moon is not in a perfect circular orbit around the Earth. It's probably slightly elliptical, but on average, 380,000 kilometers distance, which would be close to 250 miles distance, 250,000 miles distance, okay? So, it's our nearest neighbor in space. Maybe so close that it was actually part of us, okay? We don't know that, and you will get to that. What's special about it? It's characterized by craters. Why would there be craters there? Say again? No atmosphere, so all those meteors and meteorites and stuff that would have been burned up in Earth's atmosphere, or Jupiter's or Venus's, not on Mercury or our moon or most of the other moons. They are going to get pounded with these things. So lots of craters. Okay? You have what they call the lunar highlands, and then we have the Maria. Now, where that came from, early times of looking at the moon, the Maria looked darker because they were under the shade of the highlands and whatever, and people thought they were seas, marine, Maria. Okay? So that's why they named them that. Actually, they think these darker things are ancient lava flows. So not only were they in shadows, but they were also dark because they were lava flows. So obviously at some point in the moon's history, it had volcanic eruptions. Not anymore. So the craters are related to the fact that the moon has basically no atmosphere at all. Now, the moon was the subject of 12 Apollo missions. Okay? And let's see. Here is a picture of the moon, and you can tell this picture was a composite of several other pictures taken and they put together. But the highlands are the lighter areas, and the darker areas are what they call the Maria. Okay? Ancient lava flows. I think I said that right. Okay? The light-colored lunar highlands, smooth and dark Maria, and many craters. I mean, bunches of craters. This isn't very close, but you can see craters all over the place there. Just speckled with craters, like worse, well, just lots of them. Okay. Now, total of 12 Apollo astronauts walked on the moon. Now, that's different from 12 Apollo missions, because some missions had none and some had multiple. Okay? I think the next slide I thought listed those. It didn't. Okay? You can find them on page 424. Now you see Apollo 17 is listed. There were 17 missions, but not all of them went to the moon. Some of them were practice missions. And then there's an 18th one listed, the Apollo Soyuz mission. And what they did there, Soyuz had been the Russian space station, and it got damaged, so we sent an Apollo craft to help them do the repairs. I think that was the story on that. Apollo 1, however, didn't make it to the moon. Anyone know why?
It exploded.
Yes, it exploded. The crew died in their spacecraft during a test 3 weeks before it would have flown into space. They were just testing it to see if things were working right.
This one, all those people got on there.
Okay, that was a later one. Now, I think you're talking about the space shuttle. There were 2 shuttles that also exploded. This was earlier than this. These were 3 astronauts. Now, what city, I'll give you a hint, in Alabama is closely related to the space program?
Oh my gosh,
Huntsville. Okay? And speaking of which, here is Shikaya. Okay? Has anyone else come in since I called roll? I haven't caught anybody, but some people, there's been so much coming and going, I may have missed somebody. Okay? Now, Huntsville very close to the space program. And when that first Apollo blew up, sitting on the ground, not even getting close to ready for launch, that really affected people in Huntsville. And the commander of that thing was Gus Grissom. Guess what the next high school built in Huntsville was named? Grissom High School. The number 2 man on that was Ed White. Guess what the next middle school built in Huntsville was named? Ed White. And the 3rd guy on that was Roger Chafee. Guess what the next grammar school built in Huntsville was named? Chafee Grammar School. I think all 3 of them are still there. Grissom has moved locations, but my wife graduated from Grissom High School. And her brother, my brother-in-law, and her sister, my sister-in-law, all graduated from there. Long story, sorry. Probably the most famous Apollo, if you don't count the one that blew up, Apollo 1, was Apollo 11. What was it so famous for? What? One more time. Yes, exactly. And not just Neil Armstrong, but I think Mike Collins did too, or Buzz Aldrin. Buzz Aldrin, I think Collins was still on the orbiter. He was the commander up there. So yeah, that was the first moonwalk. That was that. The next most famous one, perhaps, was Apollo 13. That one's actually been made into a movie. What was special about that one? What's that? Okay, no, that was the space shuttle. Okay, Apollo 13 was an abort in deep space. They were in the process of doing the mission, and things went completely haywire, and they had to get out of the space vessel into the little module and drive that back to Earth. And that was an amazing feat of skill and adjustment on the ground and everywhere. Second, they did not know. They were stuck out there, and they were never knew if they were going to get back or not. Their families didn't know if they were going to get back or not. It was amazing. So they, Opie, what's his name?
Ron Howard.
Yeah, Ron Howard was the director of that Apollo 13. Quite a movie. Okay. All right. That, I think, covers the moon. I mean, that part. Let's now look at compositions and features of the moon. All right. Now, this is a little maybe hard to believe. The top, approximately 3 meters of the moon, is a fine gray dust. Okay, what is a meter? About my waist. 2 meters would be to here, 3 meters would be about the ceiling. This whole room, most of the surface of the moon, 3 meters of fine gray dust. If you were walking on that in regular shoes, you're in bad shape. The astronauts had on big, wide boots so they could not sink down there. Now, why? Fine gray dust accumulated from micrometeorite impacts. So it has been pummeled over its whole lifetime, billions of years, by meteorites. Okay, they all hit the surface, and they either break up the surface of the moon, or they are very small meteorites that are hitting that. The glass beads are formed from the melted material. That stuff comes in at such a high rate of speed, it melts on impact and then recondenses into these glass beads, fine gray dust. Now, the rocks are basalts. Now, we haven't hit basalts yet. We'll hit that in the next chapter. Basalts. Basalts are formed from molten lava, just about always. Okay? And we'll talk about features of basalts in the next chapter. That's what most of the rocks are. The light-colored highland rock were formed about 4 billion years ago. 4 billion years ago. The dark-colored Maria rocks, which are formed from the molten lava, they range from 3.1 to 3.8 billion years. So the light-colored highland rocks were the earliest formations on the moon, and then the molten lava, in other words, the seismic activity, the volcanic activity, happened about 200 million years later until about 900 million years later. So that was the time of active volcanoes, the dark-colored Maria rocks. Okay? Now, what's the internal structure of the Earth? This is one of those weird facts. The internal structure between 65 and 130, which is exactly double, okay, kilometers of the outer rock, the thickest part is on the back side of the moon. The thinnest part is on the front side of the moon. So 65 kilometers deep of outer rock on this side, twice that much on the outer side. Then inside that is about 900 kilometers of partly molten iron core. Now, this partly molten is why 3.1 to 3.8 billion years ago you were having molten lava, because they were erupting. Now it's no longer erupting. It's fairly stable. We'll see that later. So it has a partly molten iron core, and you'll learn in the next chapter or two that's exactly what the Earth has. Okay? And then you have outer rock, thickest on the far side, thinnest on the near side. Now, here's the other feature of the moon. I think we mentioned this before. You only see one side of the moon. You'll never see the outer side. Say again? Yeah, unless you're in a spacecraft that you're doing. I haven't ever been in one. Okay. So, I'm sure they must have. Okay. I haven't seen any that I know of, but mostly what we see is always the same side of the moon. You don't always see it all because part of it's dark, sometimes part of it's light. A full moon always looks the same because wherever you are, it's always the only side you see. And the fact that it's thicker on the far side, thinner on the near side, it all supports this idea that early in Earth's formation, there must have been a huge collision and not part of Earth out in the space around it, and that would account for the fact we only see one side of the moon. And it's thicker on the outside than on the inside. What's that?
I thought one side of the moon because it's
What? Yeah, its rotation period is exactly its revolution period.
turning on its axis.
Yeah, exactly. One time around. One rotation, one revolution. But that would account if it came out of the Earth, then it would be part of the whole system. And the thicker on the outside than on the inside, that fits too. All of this seems to fit. Okay. What's that? Oh. So here's what we pieced together as we think the history of the moon has been. Way back, stage one, the origin stage. Here's the theory that it was formed from material ejected from a collision of some enormous object with the Earth. Now this was probably back when the Earth was still mostly molten, not solid yet, but it may have been later, okay? So that's the origin. Now, stage two, the molten surface stage, when that happened, that had to have been a very major collision, very hot because of all the friction, so the surface was molten, completely molten. So the molten surface was about 100 kilometers deep, okay? About 200 million years after formation, remember the 4 billion to 3.8 billion. That's 200 million years. That was the molten surface stage. The heating from the solar system debris impacts. One of those is what formed it, okay? And more of those. Okay. Stage 3. It goes from a molten surface to a molten interior. That's accumulated heat from radioactive decay, because all of us were made from remains of some supernova in the past that was all very reactive, very radioactive material. Now here, I think they've got their letter wrong. Remember on the previous slide, there's 3.8 billion to 3.1 billion. These M's should be B's, not M's. Okay? And in your text, that's verified. You'll see those are B's there, not M's. So 3.18 billion years to 3.1 billion years. And then this should also be a B there. Okay. So, the origin is when there was some huge collision and it burst off. Then it was a molten surface. It was so hot from that collision and other collisions that it was melted on the surface. Then slowly over time, about 200 million years, it took to cool down the surface enough to solidify, but she still had molten interior. Ever since then, stage 4, for the last 3.1 billion years to present, that the moon has been basically cold and quiet. No more, I mean, they have a little bit of lunar quakes, moonquakes. You can see those happening a little bit, but there's no active volcanic activity that we can tell at all. Okay? The surface is now scarred by micrometeorites and meteorites as they hit the moon after its surface solidified. Okay? That's been the last 3.1 billion years. So this lasted about 200 million years. This lasted, that happened. This was about 200 million years. After that, another 700 million years, with, stage 3. And for the last 3.1 billion years, nothing. Just become. Okay? Except lots of collisions. All right. That's the history of the moon. There is a picture in figure 1628 in the text of some of those craters that have been formed by all those meteorite collisions. All right. Any questions on the history of the moon? Everybody got it? Okay. Now let's talk about the Earth-Moon system. This is 16.5. Okay? And I've mentioned this several times before. Say it again. It's pretty important. The Moon-Earth mass ratio is the largest in the solar system. Sure, there's larger moons, but not by a lot in the solar system, but they're around enormous planets. The Earth is a pretty small planet, and yet our moon is a pretty good-sized moon. So that Moon-Earth mass ratio is the highest in the entire solar system, which probably indicates that collision must have occurred, which must have been a major one. Now, its diameter is about a quarter that of the Earth. Okay? So if Earth was like this, it would be a quarter of that. It seems pretty small, but it's no other Earth-Moon, planet-moon system is anywhere close to that. The mass, though, is only 1/81st that of the Earth. Because if you quadruple the mass, then you quadruple the diameter, going from 1/4 to 1, you multiply that by another 4, that would be 64 times. So, and then the Earth is denser in the middle, so yeah, that makes sense. About 1 81st that of the Earth. But still, by far the largest in the solar system. It's large enough to affect the Earth's orbit. I think I mentioned this before. Because the moon is so massive that it makes the Earth sort of wobble like this. If the moon goes here, the Earth is doing just a small wobble. The moon's moving big time, Earth moving just a little, but it does affect our orbit. Nothing major, but it does affect it. The Earth and Moon rotate about a common center of mass. I think that's what they're going to show here. Now, the first up here is not what's happening, okay? What this shows, what if the moon had negligible mass compared to that of the Earth? Then the center of gravity would be right down the Earth. It wouldn't matter where the moon was, the Earth would follow that path. But because our moon has such a large mass, our center of mass is over here. The center of mass between the Earth and the moon. We're so much bigger that it's definitely on our favor, but the moon does influence. So therefore, when the moon spins around the Earth moves a little bit around that center of mass. So you see when the moon is over here, the path of the Earth is like that. When it's over here, the path is here. When it's over here, it's here. So it makes us do a little bit of a wiggle jiggle when we're going around. Not a major change, but just a little. Okay? Now, phases of the moon. This is going to be the major part of today's lab. Not going to spend maybe too much time on it. We'll spend enough time on it. A lot of time we're going to spend on what you're going to do in the next couple of weeks or so. But the phases of the moon is another part of today's lab, and that's going to be the biggest chunk of the lab. It's a result from the changing relative positions of the Earth, the Sun, and the Moon. Okay? Let's start with the new moon. Okay? Oh, I didn't see Katie come out. All right. Now, when we see any part of the moon, what we're seeing is light reflecting from the sun off the moon and coming back to Earth. So everything depends on the relative position between the Earth, the Sun, and the Moon. A new moon means the moon is over here, or something like that. We don't see any light because the sun's there. Tarshish is the sun, remember? And we see only the dark side of the moon. So basically, we don't see the moon, okay? Unless you happen to have a certain time. Now, guess what time of day the new moon is up there? There's the sun, new moon. It's going to be in the daytime. Another reason we don't really see it much because daytime is really light by the sun. But every now and then you'll look out in the day and you'll see the moon there. That's probably very close to a new moon. Okay? So that's your new moon. Your first quarter moon is when the moon is over here. Let's see, first quarter. It would be here. So now we see just half of the moon lighted because only half of it is toward the sun. The back half is dark. Here we only saw the dark side. Here we see half and half. That's the first quarter. When the moon's over here, we see the full moon, completely lit by the sun. That's the full moon. The last quarter is when it's over here. And again, it looks just like it did over here. The side toward the sun. Thank you. Y'all awake yet? Okay. Okay? When the moon's over here, we see lighted half, dark half. So we see, it's kind of a weird nomenclature because sometimes this first quarter we call a half moon. What are you doing? Throwing out my earth around, huh?
Also, I think you're.
Okay. Let me get that, because that may make it slick here. If you would, thank you. Because that could be slick and someone could slide on it. I guess this came down too, didn't it? I don't even know what this is. Or was this his? I don't know. No, I'm going to throw that around some too. Okay. If ever anyone needs any hand sanitizer, we got plenty of it up here. Well, not. You're welcome to use it. This pump doesn't work. You'd have to pull it out and like it. Okay. So this first quarter moon, we often call a half moon. Because only half of the moon is lit. The third quarter moon is also a half moon. This is a full moon. That's a new moon. And here's what I was just saying. The same side always is facing the earth. Whether it's a new moon, that's what's facing the earth. A half moon, that's what's facing the earth. Yeah, it's the same side. You only see portions of it. But it's always the same side facing the earth. Okay. Get this figure down. Plan it in your mind. Okay? This is what we're going to base most of the day's lab on. Thank you so much. Is this a figure like this? Now, there's going to be one major difference between this one and the two major differences. Okay? Here's what they'll be. For some reason on the lab, they have the sun over here. So everything is reversed. Okay? Everything is reversed. Okay? Number two, they're going to show a moon here, 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 and here, as well as those four positions. So we're going to see 8 possible locations of the moon. Now, other sort of issues, this is obviously not to scale. Okay? The moon, the Earth is 4 times bigger diameter than the moon. This one's, that looks like greater than half. So, yeah, the scale is not right, but what you see is right. Okay? Always a half of the Earth, planet, moon, whatever that's facing the sun. Only the half facing the sun is lit. Remember, in today's lab, the sun will be over there, so this side will be lit, and this side will be dark. Okay? So the new moon is when the moon's on the same side as the sun. Okay? So the half that's lit, we don't see. The half that's not lit, we do see. As it moves down here, then we'll start seeing just a little bit, a sliver. We call that a crescent moon. And it gets bigger and bigger until it's a half moon here, which is also called the first quarter moon. Weird naming. Okay? And then when it gets over here, then this moon is getting bigger, more lit every night. We call that waxing. We'll talk about that in today's lab. When this is a half moon, this is a crescent here. When it gets more than a half moon, but less than a full moon, we call that a gibbous moon, Gibbous. We'll talk about this in lab. And it's still waxing because it's getting bigger every night. When it gets to be a full moon, it's no longer waxing or waning because that's max. Okay? And then the next night, it's just a little bit less. Still a gibbous moon because it's more than half, but now it's a waning moon because it's getting a little bit smaller every night. Then it gets to half moon again on the last quarter, and then it starts getting smaller starts with big crescents, making smaller and smaller crescents until it's just a tiny little sliver that you see, and the rest of it is completely in the shadow. This would be a crescent moon waning, getting smaller every night. New moon again, neither waxing nor waning. Yes.
We're in the middle, right? Earth is
Earth is in the center.
Okay, it's in the center. And it begins with the new moon?
Whatever it is. You know, if you go out and look tonight, I don't know what it is tonight.
Okay.
Wherever you do it. I just started this one. You could start anywhere you want to. It's a complete cycle.
I thought it was because of the different times of year, the seasons. January and.
Now, actually, every month has one complete cycle of the moon.
Okay, so it doesn't matter.
And that's why it's a month, because it's based on the moon. Yes? That's a good question. I'm pretty sure the moon does have a little bit of a tilt. Most things do. So therefore it would. But since there's no atmosphere and no life, who cares? Okay? But yeah, it probably would have hotter and colder and basically the side toward the sun is probably pretty hot and the side away from the sun is frigidly cold.
But actually the phases of the moon is like the new moon, the first quarter moon.
Mm. Yeah, those are the phases, and they all depend on how much of the lighted moon we see. Here we see none of the lighted moon. Here we see just a little bit. That would be a crescent. So we see half a lighted moon, and that's the first quarter. Then it's more than half, getting up to a full moon. That's gibbous moon waxing, then gibbous moon waning back to a half, and then a half moon waning back to a new moon. So that's a waning crescent. We'll talk about these in lab more. All right. Any other questions? Good questions, by the way. All right. Anytime you see a crescent or even a gibbous moon, you can guarantee the sun is at the thickest part of that moon. That's the direction to the sun. So if you go out tonight and you see a crescent moon, you know the sun is down this way. Can't possibly be exact there, otherwise that would be lit. So the sun is on the lit side, the thickest side, and you can draw your connector between the tips here and make it perpendicular through the thickness. That's where the sun is. And toward sunrise or sunset, depending on when you see this, you can tell exactly where the moon, the Earth, the sun's coming up. Okay, because that's going to be there. Okay. Now, that's the same verbiage on both of those. Now let's talk. Oh, okay. There is another little blurb here: mistakes and misunderstanding. This curvature you see here is not from the shadow of the Earth. That's the fact that only a little bit of the moon is being lit by the sun. That's the little bit we see. The other half of the moon is being lit by the sun, but we can't see it. That's on the other side. But this is the only part of the lit half of the moon that we're seeing. Yes?
So new moon is when you can see.
Yeah, that's when the moon is between us and the sun. So the lit side is over here. Half the moon is lit. We don't see it because it's on the other side, you know, and we only see the dark outline of the moon, basically. Okay, now that's a different issue. That's what we're coming to next. That's exactly another issue. And we're going to get to it. Next thing. Let's hit these mistakes and understanding. Okay? Have you ever heard once in a blue moon? What do we mean by that? What's that? I can't hear it.
We have every sometimes. We have a blue moon sometimes.
Okay. Okay, and not very often. Here's what a blue moon is. It's in reference not to the color of the moon. I don't know why they call it blue. Instead, it's a reference to an extra full moon that occurs in a season that normally has 3 full moons. Because you see, you have one cycle every month, but remember that was once every 29 and a half days. So every now and then, you'll have a month with 2 full moons. That would be a blue moon. That second full moon in that month. Doesn't happen often. Usually there's only 1 full moon a month. But because it's 29 and a half days, and some months are 30 or 31 days, it could be you'll have 2 full moons in 1 month. But that doesn't happen often. Very, very rarely. So that's what they mean once in a blue moon. Now,
So blue moon is extra full moon.
extra full moon in a month, or they say in a season, okay? Usually a season has 3 full moons because there's 3 months in a season. If you have one season with a 4th moon, that's the blue moon. So that month would be 2 in 1 month then. So it's the same thing. All right. Now this I tend to sort of disagree with because I've heard so much. A popular myth has more accidents happening during a full moon phase. They say that doesn't happen. However, I think I've heard from enough people in emergency rooms and other places like that, that something goes on full moon. They say they have more activity. We had a neighbor who was sort of nuts. He, at one time, poured acid on one of the other neighbor's cars. He threw rocks through our picture window. He called the police on other neighbors, and it almost always happened right around the full moon. And we don't know why, but if you think of the word lunatic, that comes out of lunatic. People have observed this over the years, centuries, millennia. Yeah.
So, it's an interesting story. My grandmother, of course, all y'all would know, in the day when we used to tell when babies are coming through the moon. So my mom was about to have my brother, and the doctor told her that he will be born on June 12th or 13th.
Right.
So my grandmama said, she's gonna come early. So what she did, she went outside the hospital and she looked up at the moon.
Right.
And the moon was at a crescent, looked like a cup tilted over. And she said, well, a lot of babies gonna be born tonight. And exactly, my brother was born 11:47 or 45, June 11th, almost June 12th. But she said June 12th.
Right.
But she wasn't that far home.
Right. Right. And there are some things. I know my dad, he was a farmer. He used to say when the moon did that, you expect to have some rain. I don't know if there's anything to it, but it's sort of like it's got water in it. When it tilts like that, you're going to have rain. Is that right? Okay. It's amazing. Okay. So anyway, let's go on to eclipses, what you were talking about of the sun and moon. Now, the moon's orbit is inclined about 5 degrees from that of the Earth. So that means most of the time the moon is not in the Earth's shadows because it's got a 5-degree tilt far enough away that 5 degrees makes quite a bit. The moon is much smaller than the Earth and that kind of stuff. So most of the time it's not ever in the Earth's shadow. However, when that 5 degrees happen to cross, if you had pictured, if the moon had an Earth ecliptic and the Earth's equator, there would be twice every now and then they would cross. When that does happen, then we will have what we call an eclipse. Okay? The proper alignment of the Earth and Moon and Sun is needed. Now, it all depends on the shadows. Okay? Now, I'm going to show you this diagram, and I wish they had done it a little bit better. Okay? But this part is correct. The moon always has a shadow here. The sun is over here, it's shining on the moon, and there's a shadow back here. Okay? I wish they had shown in the same diagram, the Earth has a shadow. Now, the Earth being 4 times bigger than the moon in diameter, it has a much bigger shadow. It goes much deeper. Okay? Now, because of this 5-degree difference here, most of the time the moon's shadow doesn't ever do that. Every time it's here, it's not ever going to hit the Earth because the Earth is here. Okay? It's only when the moon is here and this point is here, then the moon shadow would hit the Earth. That's what forms a solar eclipse. Now, a lunar eclipse, because remember the Earth has a shadow here, it goes way bigger than that. The moon could easily fall into the Earth's shadow. Because of Earth. Say again?
Let's change to a red orange color.
Yeah, and the reason for that is what you get is reflection of light from the Earth hitting the moon and coming back to it. It does get sort of a reddish color. Okay. So when the moon, okay, this is the plane of the Earth's orbit, and this is the plane of the moon's orbit, only when they're very close to crossing, and this cross is directly between the sun and the Earth, or directly behind the sun and the Earth, then do you get eclipses. The solar eclipse here, the lunar eclipse back here. But because the Earth's shadow is much bigger, you're far more likely to get a lunar eclipse and last for long. Those conical shadows have two parts. And the next slide, I think, shows this a little bit better. So let me go to the next one. Okay. Now, again, the scales are off. The sun is so much bigger, but it's so much further away. So they brought it in and made it smaller. The umbra, the darkest part, umbra means black, okay? The blackest part of that shadow will sometimes touch the Earth, sometimes not quite touch the Earth. It's a very small area. Remember when we had the solar eclipse about 3 or 4 years ago, wasn't it? Okay? It was only a very narrow band. Nashville had it, we had just a partial. We were over here, and Nashville was right there. Okay? And it went up across the country. Out here is called the penumbra. That's not as dark, because some of the light rays from the sun does come here. Here, none of the light rays come. So that's the dark part. That's the umbra. The light part is when you're in a partial shadow. There you'll get a partial eclipse of the sun. And that's what we got in Birmingham. We were right around in here, so we got a mostly eclipse, but not a total. Nashville was right there, it got a total. Okay. Now, the umbra is the inner cone, complete shadow. Penumbra is the outer cone, which is a partial shadow. Now, a solar eclipse is when the umbra touches the Earth. Now, as you see here, the way they've drawn it, it just barely touches the Earth. When it doesn't, when the moon is further away from the Earth, which remember it does, it's an elliptical orbit, sometimes it's closer, sometimes it's further. If it happens to be further away when you have a solar eclipse, then the point doesn't quite reach the Earth. And then you have what they call an annular eclipse. You see a ring around the moon, very bright ring. And the umbra doesn't quite reach the Earth, but you're directly under that, you see that. I can't remember if the one that hit a few years ago was annular or not, because I wasn't in it. It was? It was total eclipse, not with a circle around it. Now, okay, what time is it now? It's what? Okay, it's a good time for a break. You want it? Okay, I know several people have had to get up and take one, which is fine. At 3:45, we're going to stop and go to the lab. I think we'll make it. That's sort of why I was rushing to it, to make sure we did get to it. Okay. The lunar eclipse is when the moon is engulfed by the Earth's shadow. So if you continue drawing the Earth here, and then drew its conical thing, it's easy to see why the lunar eclipses happen far more frequently. Okay. Now, here are total eclipses visible from the U.S. between 2010 and 2025. So some of these have already happened, some we'll have in the next 5 years. The last one we had was 2017, total solar eclipse, and that was from Oregon to South Carolina. That's the one that went through Nashville. Okay, August 21st, right after school started. I mean, huh? You were,
Our teacher just stopped us from doing our work.
and we were. I did too.
Where?
Huh?
What happened?
When the last total solar eclipse. We didn't have a total here, but we had a partial. We went out and watched it. Okay? The next one coming up is April the 8th, 2024. That's about 4 years from now. I'll be retired, so I'll be able to watch it if I want to. Okay? If I'm still around. Huh? All right. Total lunar eclipses. You'll see you got way more of them. You had 2 in 2014, 2 in 2015, then you went a couple years without it, 3 years without it, then you had one in 2018, 2019, that's just last year, and the next one coming up, not this year, but next year, May 2021, and it'll only be visible at moonset, okay? Now, lunar eclipses happen when it's a full moon and the moon passes in the Earth's shadow. So that time, that is the Earth's shadow. The phases of the moon is called just by the curvature. Okay? Now, solar eclipses, it's always a new moon because the moon's on the same side. We're seeing the dark side of the moon, and the sun is being eclipsed by that. Okay? So the next one coming up, we had one last year, January 21st. Well, the next one will be 1 year from now, May 2021. Then we'll have another one in 22 and one more in 25. Okay? So you see you had 9 lunar eclipses for every 2 solar eclipses. That's about the right ratio. All right. The next subtopic here is tides. Okay? That's not the crimson variety. This is the ocean variety. Now these result, let me go on and get a slide up there. These result from different gravitational pulls on the front and back of the Earth. If you think about the Earth, we are a little bit solid, but our surface is mostly liquid. Okay? And because of the gravitational pull, let's say the sun is over there, it's pulling and it pulls the water that way, okay? The solid part of the Earth is here. It's pulled a little bit that way, leaving behind some, okay? Some water. So you have the thickest tide change when you have the sun over here and the moon over here, or both the sun and the moon here. That's what gives the biggest tides. So when the Earth, the moon, and the sun, okay, result from gravitational pulls in front and back of the Earth. The 3 factors that influence the tides are, first, what is the Earth's, moon, sun position? Now, spring means biggest. That's when the sun, moon, and Earth are aligned. Sun's out here, Earth's here, moon's here, Earth's here. That's the greatest pull on the water on this side. But equally, when the moon's here and the sun's there, that's when, those are the spring tides. When the moon and the Earth, when the Earth, moon, and sun are aligned together, either on that side or on both sides, okay? That's your spring tide. The neap tides are the least, and that's when the moon's up here and the sun's over there, or vice versa. That'll be the thinnest tide. That's your weakest tide, because the moon's pulling this way and the sun's pulling that way. They're at 90 degrees of each other. Now, as I've already mentioned, the moon goes around the Earth, not in a perfect circle, in an elliptical orbit. So the greatest pull is when the moon is closest. That's the perigee, closest point. The less effect when it's at the apogee. That's the farthest point. And there's a 48,000 kilometer difference, which is about 31,000 mile difference. Okay? So it can make a significant difference. Now, the electrical orbit. So the alignment influences the tide. The electrical orbit of the moon influences the tide. And then the size, shape, and depth of the water basins, that also influences. The lowest tide variation is on the Gulf of Mexico. Great big old pond, I say, and very gradual shape, drop off, size, shape, and depth, not much difference. And you only have a third of a meter, which is about a foot.
That's the only place that doesn't experience a lot of time.
Say again?
That's the only body of water in the world that doesn't experience.
Not the only one, but the major, the least effect is the Gulf of Mexico. The greatest, the Bay of Fundy. I think that's up in Nova Scotia. And that's a very narrow channel, so the shape, very deep, and maybe it's not deep, maybe it's shallow, I don't remember. And the size of it, 15 meters? Now what did I just say? This floor here is 3 meters. So that would be a 5-story building. That's high tide to low tide. It goes up and down like a 5-story building. How in the world do you have a dock on something like that? They have to have a big old pole for everything to move up and down. That would have to be crazy. Yeah. So really big difference there. Now, that's the last slide. There are 2 more examples here. It says, how long does it take a reflected beam of light to travel from the Earth to the moon? Blah, blah, blah. Why would they have that in the tide? Let's not even mess with it. Well, the answer is about 2.5 seconds. Okay? Does it take a reflected beam of light to travel from Earth to the moon and back again? And they have actually set up one of the Apollo missions, put a reflector on the moon, and they have measured the distance from the moon by how long it takes light to go back and forth. They actually did that. How far away is the moon if the reflected beam takes that long? So that's just doing the same thing in reverse. The person behind the science that they mentioned here is Carl Sagan. Now, I don't know if any of you remember him. He did a public television program called Nova, I think it was. And he was a great communicator of science. He was a good physicist for sure, but his major accomplishment was how well he communicated science. And this is a picture of him. My older brother just loved Carl Sagan. I think he read every book he ever wrote. So anyway, he did major research and did good research, but he was far better communicator. So if you want to write on him, you can, but remember, this blurb is not your source. This may be the source of ideas, but you have to get your source outside the book. That finishes chapter 16. Now, I say this every chapter, nothing replaces reading the book. So now that you got your books, please read them. But once you've read the chapter, I would say a time or two, depends on how well you read, then you have a summary. Now, this is one of the longer summaries, I think. It has a lot of different words in italics, which will also show up in key terms, and that's a pretty long list of key terms. Now, these are alphabetical. You can find them on the pages indicated where they're first mentioned or first defined. But the best thing to study for your test, I think, is the applying the concepts. These are not the same questions you'll see on the test, but they're hitting the same material. So if you can understand these, you got it. They have 47, which is about average, but they have all the answers. Okay? So if you can do those without looking at the answers, and then check yours by the answers, figure out why you may have missed it. If you can't figure out why you missed it, maybe it's wrong, but bring it into class and we'll talk about it. It'll be a great thing to do to study for the test. Then you have questions for thought, This is a lot of them. Goodness gracious. There are 30, which is one of the largest group I've seen. Those are good things to study for the test. They don't have the answers given, but if you're interested in finding the answer, bring those questions to class too. For further analysis, 6, that's about normal, maybe 1 or 2 more. And then the parallel exercises are a lot like the examples in the text. A lot of times they're just not, they're sort of made up concepts. But, I mean, they're true, they're all good, but they don't have the answers in the back. They're supposed to, but I think when they published this new book for me, I said 2 things I wanted. I wanted 3 things. I wanted the physical constants. The first time they did this, they didn't put those. And I said I wanted a periodic table. The first time they didn't put it. It was in chapter 8, but our class doesn't do chapter 8, so I wanted a periodic table. And the third thing I wanted was the group 8 answers that are in the back of the big book. I wanted them in this book, in your little book. They didn't put them there. They did the other 2, but they didn't do that one. So you don't have to worry with parallel exercises unless you're just interested in doing those problems. You just can't check the answers, but you can still compare it to the examples in the book. All right. Any questions? All right. How's our time? Second? 3:30? 3:34. Okay. Now, we can either continue in chapter 17 now, but if we take a break now, then when we hit 3:45, it doesn't make sense to have 2 breaks. So you want it now or want it at 3:45? You choose. Now? Okay. Let's pause this. I'll go on and get out of this. Discard that. Y'all can go on your break, and then when you come back, try to keep the break less than 5 minutes if possible. And when we come back, we'll start and just have a very short introduction to chapter 17. Then we'll do the lab. Was there a question? Okay. No.
Yeah. 4 hours sitting on chairs.
Okay. Only got about 4 minutes here. We've just finished the astronomy part of the course. That was the universe, solar system, and Earth-Moon system. Okay, those 3 chapters, 14, 15, and 16. This is starting what you might call the Earth science, but more specifically geology portion. Okay, and we start with rocks and minerals, chapter 17. And they have a beautiful picture of some crystals of some mineral here. I think they give it rhodochrosite or something like that. At least the one in my book is that. It's a little different from that, but I believe it's about the same. Okay? The core concept here is the Earth is a dynamic body, meaning it's always changing, that cycles rocks and minerals through ongoing changes. Okay? This happens to be a rock we'll talk about in the last half of the chapter. That's probably one of the oldest rocks that we've found so far on the planet. Probably close to 3 or 4 billion years old. You can tell it's undergone a lot of changes because everything you see here that's a band was at one time horizontal. And it has gone through so many changes and pressures and temperature changes. It's warped and bent and crossed up. That rock scene a lot. Okay? We'll talk about what the minerals and rock name are later in the chapter. Say again? Oh, okay. This is chapter 17. So, 17.1 will be talking about solid earth materials. Now, why solid earth materials? Like I just said a short while ago, Most of the Earth's surface is covered with liquid, water, the oceans, of the solid Earth materials, which are the landforms, but also, guess what? Underneath the oceans is solid Earth material. So we're talking about the whole Earth. It's just that some of it we don't see, okay? The solid Earth material is a non-uniform distribution of matter, okay? And you can almost tell that just going out. If you drive from here to Red Mountain, you'll see land, you'll see rocks, you'll see, it's non-uniform. Nothing is there. But also if you go down through the Earth, you find there's even bigger changes. In the very center of the Earth is a molten core, meaning melted core. Absolutely, well, mostly liquid. Okay. It contains the most heavy elements. Okay? This is why I wish, yes. Is it? That's why I wish we had the periodic table in your book. Most of the elements down here would be found in the core. Now, the main part of the core is iron and nickel, which are right in here. Okay? But most of these other heavy things are found in the core as well. So basically we'll start over with this slide next time because there's a lot in it, and we'll pick up here with solid Earth materials next time. Say again? Okay. Okay. Everybody got it? All right. We'll pause here. Well, wait, we won't really pause. Let me just close out the PowerPoints. And I'm going to pick up this PowerPoint. And while that's coming up, I'll pass out the labs. Now, if anyone's here who needs some earlier labs, I'll pass those out as well. Okay. Is anyone here who needs lab 1? Lab 1, okay? Oh. Anyone else who needs lab 1? Celestial coordinates. Now, most of the lab I think you can do just by listening to the YouTube video, okay? And I think I labeled it which one had lab 1. Now, in lab 1, we didn't quite finish the lab on that one, so the next video after that, you'll hear the last part of the lab. It doesn't say that. Okay. Now, there's still a few people who haven't taken test 1. Yeah.
Can I come in my lab?
Yeah, sure. I'll take it anytime. Here's another thing I meant to say at the first of class, so let me go and get it off my chest now. I'm behind in grading. Sorry about that. But I hope tomorrow morning, I doubt if it's going to happen, but I hope tomorrow morning to have most of my 4 hours office hours able to catch up on the grading. Now, I have a feeling I know what's going to happen. I'll walk into the office. I usually get there before anyone else, so I'll get started on grading. Then when everybody else gets there, I bet you we're going to have to do contracts tomorrow. I bet you we're going to have to do a lot of messy stuff tomorrow, so I may not get it all done, but maybe over the weekend. Is anyone wanting to take test 1, the chapter 14 test, on the Birmingham campus tomorrow? Some people said so. Say again? I'm on Birmingham campus tomorrow, from 8 to 12 on Fridays. Will you? I'm sorry? Today? At the end of the class? Absolutely. Does anyone need to take it on the Birmingham campus tomorrow, so I'll know to put it in my grade book? No? Okay. Then, lab 2. Anyone need lab 2? Okay. Motions of the sun, and again, you can hear just about all of it. Okay. Now, what has happened with lab 2 is that I need to make one more copy because somebody added to the class after I had these run off, so I don't have enough copies. So is it only one more person? Katie, are you the only one that needs lab 2? So right after class, hang with me and I'll get lab 2. Okay, I'm going to put it crosswise. Okay, anyone want to take test 2, chapter 15 test on Birmingham campus tomorrow? Nobody? Okay. All right. So we're ready then for today's lab. And here it is. Phases of the Moon is the title of it. That's mostly what we're going to do. So there's a few other things we'll be doing as well. Somebody there? Okay. Hopefully they're coming back. Any other? I guess she may be coming back. Is this one coming back? Looks like maybe. All right. Jacob, was that your folder?
Yes.
Oh, it is. Okay, good. I thought that was something that fell off the desk. I said, nope, that's nothing that I ever had. All right. So, as I've said several times, this is a little bit different kind of lab than any other lab in that you're going to work on it for the next couple of weeks. Okay? What's that? Yeah, I'll explain all that. Okay? It's not going to be solid for a couple weeks, so it will take a little while. Okay. Is this in your way? I don't need it anymore, but I was just going to not mess with it. All right. Okay. Now, they have some interesting talk here at the beginning, and you're welcome to read it. I'm not going to read it to you. But just all the different things, the mention of lunatic, moonshine, all the different things we associate with the moon. Okay? If you've ever noticed certain other cultures, Jewish culture particularly, the Muslim culture, and probably some of the possibly African, but certainly Asian cultures, may do a lot more with the moon than we do. If you notice, a lot of countries' years start different than we did. In fact, I think this week is the beginning of the Chinese New Year, okay? And that's based on the moon, somehow, okay? So lots of things vary. Now, what you're going to be doing, did you get a copy of the lab? Okay, good. You're going to, at the very bottom of page 379, you'll see this sentence starts. Using about 6 observations. Now, some of you may be able to get more, maybe less, but about 6 observations over a 2-week period, 2-week interval, you will examine how the moon changes 2 things. Its position in the sky relative to features on Earth, but also its position in the sky relative to the stars. So those are the things that you're going to be noticing over about a 2-week period. Now, here is, there are some problems with this. Number one, we're on a mini-term, okay? So we do have at least 2 weeks left, but whether you have 2 consecutive weeks of being able to see the moon, I'm not sure. If we're right in the halfway through one cycle of the moon, then you have to wait 2 more weeks before you see the first half of the cycle. And I think we may have 4 weeks left, so you could probably do it, okay? But may not get a full cycle continuous. So here's part A, what your observations will be of the moon. Okay? Complete cycle of lunar phases requires about 29 and a half days. You will follow the moon for at least half of a cycle, because half of the cycle you'll be able to see the moon. The other half you won't, because it will be behind you at a given time of day. Okay? Now, during that time, so you'll make observations spread over the course of about 2 weeks. Okay? About 2 weeks. During that time, you'll be reporting 3 different things. Okay? How much of the lunar disk is illuminated, in other words, the phases of the moon. That's one thing. Also, the position of the moon relative to 2 different features. Number 1, the landscape of where you're watching. And number 2, the stars that are up there. Okay. Now, there's problems with all this. Okay. So, here's the first thing you've got to do. Whether the moon's out tonight or not. Now, if it's raining tonight, don't go out there. And if it's super cold, don't go out there. But I think tonight's supposed to be a pretty decent night. If not, wait till you have a pretty decent night. Then go out there, find your location. That's the first thing to do, choosing a location for your observation. Okay? And I would say with this is also the time of your observations. You need to do both. Let me give you one example that worked really well for one student. I had a student in this class, a very good student, who happened also to be the work study student for the evening coordinator here at the college. Okay? So he got off work about 10 o'clock every evening. So as soon as he got off work, he went out into the parking lot and made his observation. He always knew he'd get off at 10 o'clock. He could make his observations then. And he could do it from our parking lot. Okay? So what you need to do is determine, number 1, what time you can make your observation. It's going to be pretty close to the same time every night. You're not going to observe every night. So every night you're observing, but you're about the same time. Now, if I were doing it, I would make it probably 10 o'clock, because that's what time I try to put the dog out. Okay? So I know I'm going outside at 10 o'clock every night to put the dog out. So I would try to make my observations at 10 o'clock at night. Now, some of you are super big early morning people. My wife, she's asleep by 9, okay, or awfully close to it. But then she's up by 4, okay, or 5. She can't get her sleep cycle right, okay? So she might choose, if she were going to do this, to go out early in the morning. Now, probably not this time of year because it's so cold early in the morning. But if she were going to do this, say in a warmer time, she might do that. So you pick the time that you know you could be at this, whatever site you choose, every night at that time. You're not going to do it every night, but you do need to do that. So they say first choose the time of spot, but you do that with the time that you know you could be there. Now here's what that spot needs to be. A relative unobstructed view of the horizon and sky. Now, that's a problem where I live, because we have big trees, we have Red Mountain just to the south of us. It's not a super good position. But if it's all I got, that's all I got to go on. Okay? So try to find a spot with relatively unobstructed view of the horizon and sky. Now, if you happen to live pretty close to a ball field, possibly a golf course, parking lot that's not going to be lit. You really don't want it to be lit. A parking lot that's not necessarily lit, especially very brightly lit. If you have something like that that is safe for you to go to at a certain time, either late night or early morning, that would be ideal. And most of us don't have that. So get the best position that you can find. Okay? Middle of a large open space with few low-profile landmarks is ideal. Like I say, where we live, big trees, It's not going to be ideal. You will need a little ambient light to make some sketches. Now, I don't care if you make sketches or not. You probably will find them useful, but don't sweat them too much. Now, what you need to do is do this before you start making your observations. So get you a little flashlight, pen light, or something like that. You can make your sketches. It is important that you use precisely the same location for all your observations. That's why I said find the time and the place that you know you can be there. Every night you're going to do it. You're only going to need it for about 6 observations, so that you can be there for at least 6 observations over a 2-week period, that you can be at that spot at that time. And all these other things, relatively unobstructed, very little light, all that kind of stuff. Be creative. Think about where you might be able to do this. Like I said, that guy had it really easy. Now, he had a building on this side, so it wasn't ideal, had some obstructions, but still was a pretty good place. He could go out in the parking lot and be relatively free of obstructions. But he needed to go to the same place in the parking lot. So if you're going to a baseball field or something like that, make sure you can go to the same spot in that baseball field or the parking lot. I was going to say, at one time, the mall right on Red Mountain Expressway here is basically closed down. I don't know how safe it is at night, but there weren't any lights in there. That would have been a pretty good place. It's a former mall. It's not Western Hills, but it's Western Mall or something like that. It's right down 280 here. I mean, Red Mountain, Bessemer Superhighway here. Going toward Bessemer, right before, right past where you turn. Say again?
Or that Walmart.
Okay, not going this way. Walmart's this way.
Oh,
It's
Bruno's
going this
parking
way.
lot.
Say again?
Oh, Bruno's parking lot. The old Bruno's parking lot.
It may be. I never knew what was there, but it may be the old Bruno parking lot. There was also an old, one time near that, Hardee's or something like that, but it closed down. It's somewhere around there. But that may not be convenient for you. It may not be safe. Don't go places it's not safe. Find a place you can be at a certain time that you know you can be there at least 6 times in a 2-week period within a very small time frame. Okay. You pick your time, you pick your location. Okay. Timing your observation. Now it says the instructor will give you some general guidelines. I don't know if you're a morning person or evening person. That's going to change everything. So what you need to do is you can go on your phone and find out when the moon is going to be visible in Bessemer, Alabama, in McAdory, Alabama, in Birmingham, Alabama. You pick your town, you look on it and see when the moon's going to be visible. If you can get it so it's the beginning of a 2-week period and it's going to be visible for that entire 2 weeks at the time you say. Now again, if you're doing 6 o'clock in the morning, that's going to be different intervals from 10 o'clock at night. So pick your time, pick your location, and determine when you're going to get the best shot at getting 2 weeks of moon sightings. Okay. It is critical that you make all your observations at the same time of night within 15 minutes. So if I were doing 10 o'clock, I want to make sure I get that done between, say, 9:45 and 10:15. That's actually 30 minutes, so I try to make it more narrow than that. 9:42 to 9:52 to 10:08 or something like that. When I put the dog out. Okay. Because weather may hamper your observations over the observing period, you do not want to let many clear nights go by. Now, I look out there now, and it looks pretty cloudy. Now, it may be, and I think it's going to be cloudy tonight, because we said there's going to be very little difference in today's high temperature and the night's low temperature. That indicates we're probably going to have a pretty big cloud cover. So maybe tonight is not the best night to observe the moon, but it wouldn't be a bad night as long as it's not raining to find your location and to do your initial drawings if you want to do those. Okay? Now, your first time time out, which is probably going to take about a half hour, you're going to need to get there ahead of the time you're planning to do it, but before, try to get right in the middle of that, okay? So after the first observation, which you don't even have to see the moon then, that's going to be about a half hour to pick your place and get everything done. After that, you're only going to need to be there about 5 minutes a night, okay? So try to pick tonight to start about 15 minutes early, ahead of what your normal time is going to be, and you might go 15 minutes later, about half an hour. Now, here's what you're going to observe, and you need to record these things. In order to record the appearance and position of the moon, you'll need to make, and they say a scale drawing. That'll be fun. Doesn't have to be fancy. I've had some really good artists who really impressed me with how they could draw, but you don't need that. Just a sketch. And you need to, and they say poster board, you don't need that. Just a piece of paper will do. Okay. You may want to initially go out about a half hour before the optimum observing time so you can get enough information to complete your sketch. All you need is something you can know what you're doing. So here's what you're wanting to find out. I'm going to imagine that I'm going to do it from this window. Someone said you can do it from inside. Not really, but let me do it. If I were using this as my reference, goodness, it's terrible. I was off the trees. Okay? I can't even pick out from here. Okay. See, there's a building over there with a triangle point sort of on top, right? White going up. That would be one of my landmarks. Okay. Then maybe I would pick the building back there that has a slanted roof, the only slanted roof on this campus. That may be a landmark. Then, if we're going around this way, I can't see many more, but I know right over there is Bessemer City School. Maybe the flagpole. That could be a landmark. Then if I go on around this way, I don't know, there may be a billboard near the interstate that I can use as a landmark. Then I come on around this way and maybe a tall tree. Okay? And I know that I can pick those out every night. Not the parked car, because it may not be there. Okay? That's something you can pick out every night from your spot, where at the time you're going to do, that you can pick out that thing. A tree, a building, a billboard, a power pole, a flagpole, anything such as that. Okay? Now, they give some, on page 381, some different ways to measure angles. This to me is a little awkward. Here's what I would suggest to you. You don't have to do this. If you want to use their angles, that's perfectly fine. Here's what they say. The width of your outstretched hand at arm's length is about 22 degrees. The width of your fist held out at arm's length is about 8 degrees. The width of 3 middle fingers, make sure it's 3, held out at 5 degrees. The width of your index finger held out there is 2 degrees. You don't want to get anyone mad at you, okay? So you can do that if you want to, okay? Here's what I would say to do. Take you out there a yardstick, meter stick, maybe even a ruler, a 12-inch ruler. That might be a little too short, but yeah, that's going to be as good. And hold it up and measure from the horizon to that. And just do an inch measurement, or millimeter or centimeter measurement. You don't have to do degrees, okay? But just get that. Now, use whatever makes sense to you, okay? And they say here, alternately carry a ruler and measure the dimensions and separations of the landmarks held at arc length. Okay. Now, here's what you're going to, you're going to make 2 measurements. Remember those landmarks you picked out? Okay. Let's say this one here. Now, I'm moving around so I can see them. That white triangle there, okay? The eve of the house, whatever that happens to be. What if the moon is over that? Hold up my meter stick, and I say it's 20 centimeters above the tip of that, but over here, then I turn it sideways, 3 centimeters to the right or left of that. That's what kind of observation you're going to make. Pick out your landmarks around the horizon, and then when you see the moon, pick the one closest to that and say it's so many inches or degrees or whatever you want to do, above, to the right, to the left. Okay? That's going to be how you make your measurements relative to the landmarks. Okay? So, you record the appearance of the moon at the given time, at your given location, relative to these landmarks. Pick the one closest to it and measure how far north, above, right, left it is from there. Now, if you want to get really nice about it, carry your little compass. So you can say it's north of my thing, northwest of my thing. You can do that if you want to. You don't need to, but you could do that if you want to. You may want to forget about getting the moon's size to scale over this is something else. Okay, record the positions. Now there's the second thing. First is where is the moon relative to your landmarks. Okay? The second one is where is the moon relative to some stars that you can identify night after night. The other night I looked up and I saw, I think it was Cassiopeia. It was that one that looks like a W. Now, it's supposed to be a woman in a throne that you tie down with. But it looks like a W to me. That's how I always picture that. The Big Dipper, I can always pick that one out. Orion, I can pick that out. Pick you some set of stars that you know you can find every night. Okay? And then take your ruler and say how far, if you got a compass, you know how far north or south, east or west, or right, left, or above, below the moon is from that set of stars. Pick a star. I love Orion. Orion has a shoulder and a head or something like this. He has a belt. He has a sword. Pick a star, something on the brightest star in Orion, or the tip of the Big Dipper, the last star on it, the tip of the handle, whatever. Pick a star you know you can find every night. And that W, the middle star, the left one on the bottom, whatever. Pick a star you know you can get to every night, and then record the position of the moon, how many inches or centimeters to the right, above, below, right, left, the moon is today. It would be helpful if you knew the direction, north, south, east, or west, but it's not necessary. North, south, above, below, left, or right, that will be fine. Okay. Now, you do that every night. There's one more thing that I didn't mention, and that is, what is the shape of the moon that night? Is it a thin crescent, a thick crescent, a half moon, a full moon? You're not going to see a new moon, so don't bother with the new moon. And then a gibbous moon, meaning over halfway, almost full, just over half, whatever. You're going to do that. So those are your three observations. Where the moon is relative to your landmarks around your horizon. Where the moon is relative to the stars. Some stars that you can pick out night after night after night. Okay? And the third one is what the relative shape and size of the moon is. So you record that every night, that you make an observation for about 6 nights. Okay? Now, the thing that you answer that I'm going to be grading, you've recorded all this on your piece of paper or whatever you have, then you answer this question. How would you describe the night-to-night path of the moon with respect to the landmarks around your observing site? Now, this is where it's going to be most important. If you do have a general idea of direction, have a compass, or you just have an idea. I know north is over this way. I know south, yeah. If you have a general idea, then tell me, where does the moon seem to be moving night after night? Is it moving east to west, north to south, west to east? southwest to northeast, I mean, whatever. Give me a general description that way. If you don't know the direction, it's moving, as I'm facing the flagpole, it's moving left to right. But you have to give me where you're facing. Or you can be doing this way and be right to left. Okay, so give me enough to know that you've been following the track. Number two, in which directions does the moon move with respect to the background stars? Those stars that you picked out, that pattern you picked out, and you're going to measure the moon from that, it seems to be getting closer for the first 3 days, further away to the left the next 3 days. Coming in from the right, moving to the left, something like that. Give me an idea. Going closer to it, it started low, moving up toward it, and then past it and went above it. Whatever it seems to be doing. Okay? That's on page 381, questions 1 and 2. Question 3. Actually, it doesn't say question 3. On this chart that you see right here, that is the fraction of the moon that's illuminated. So if it's a full moon one of those nights, whichever night that is, you notice it's starting at night 0, that's your first night, and going to night 20. Now, you're not going to see it for 20 nights, okay? But, you know, whenever you do, if it's a full moon on night number 8, you go right up here and put a dot by the full moon, above 8. The next night is probably going to be smaller. The next you never do it on 2 nights in a row. But then the next time you observe, it will be smaller. Or before you do that, it was getting bigger. So you should have some type of a curve here that indicates the size of the moon. 1 being a full moon, 1/2 being a half moon, or first quarter, last quarter moon. Okay. The 1/4 moon would be a crescent, 3/4 moon with it. Okay? Those are the 3 questions that I'll be grading that you make from your observations. Okay. Now, what's that? Okay. Did I ever call the roll again? I don't think I did. I should have done that. Sorry. It just dawned on me that I didn't, I don't think. Okay. Bridget is still here. Brianna hasn't made it in today. Jerome hasn't made it in today. Asia is still here. Jacob is mostly here. Okay. Kaya is, did she just walk out? Or has she been here? I don't remember. Was Kaya here? I don't know if she's been here since the break. Okay. Rakiria, I don't think has been here since the break. Justin is still here. Sholanda's still here. You're what reminded me because I thought you were going over to the hospital. Tarsha's still here. Eric hasn't made it in today at all. Zach is still here. Okay, page 2 here. Katie was here, wasn't she? That's her stuff. So I'll count her as here. Brandis didn't make it in today. Miss Lewis is still here. Antonio is still here. David was here, wasn't he? That's his stuff right there. I think he was here. Tiffany hasn't made it in today. Kaylee is still here. Donald, I don't know if he's been back since the break. I don't think he has. And Shakaya is still here. Okay. If any of the others do show up, remind me so I can mark them on the roll. Okay. Sorry about that. Okay. You asked for, go over that. If you go to page 381, bottom of the page, you'll see the first question that you'll be answering. You'll be making these observations every time. Now, let me before I get into that, let me back off to your days. Tonight, or the first decent night that you can, get out there and figure out what position you're going to be, what time you're going to be, and what landmarks you're going to use. Try to get a landmark all around the horizon. Okay? Several landmarks. Okay? That are not going to change. Okay. Now, the first night that you can see the moon, that will be your night 0, wherever that is, okay? Or night 1 if you want to make it that. I don't care. 1 or 0. And then don't go out the next night. Try to do it every other night from your first night. Because you're not going to see a lot of change one night to the other, but one night to 2 nights later you will. Now here's the deal. If that second night after your first night you saw it, if it's raining or cloudy and you can't see anything, okay, then do it the very next night from that. Okay? Do it the first, allow at least one night between, and then the first clear night after that. Then start it over again. Skip a night and the next clear night. Then the next time you make an observation, skip a night and do the next clear night. You understand what I mean? Don't try to do 2 nights in a row, but try to do every other night. If you do every other night, you may get 7 observations, okay? If you're really lucky. The odds are you won't. Especially with the weather we've been having, you may wind up with only 5 or 6 observations. Maybe fewer. Try to get as many as you can in that 2-week period. Because you're only going to see, at that time of day, you're only going to see the moon for about 2 weeks. So try to make advantage. Now, if the first time you see it, you can see it every other night for a while, but then after day 7 or 8, you don't see it anymore. You have to wait another 2 weeks till you can see it again. So then your chart is going to look something like this. You'll have a little bit of vision here and then another pickup here. You'll have a gap, 2-week gap in the middle. Okay. So now I'll get to Shalanda's question. Bottom of page 381, what you observe is where the moon is relative to your landmarks that you picked out on the horizon. Okay? So that's why I have several, but not that many, just several. And then pick where the moon is closest to the closest landmark, and then how far above it and how far right or left of it. That's your observation. You can use degrees, you can use inches, you can use centimeter, whatever you're going to use to measure. Second observation you make every night that you make an observation is pick out that pattern of stars fairly close to where the moon is. Okay? And then how far right or left, above or below the moon is from that pattern of stars. Okay? Record that every other night or every time you can make an observation. The moon will be moving. The stars are going to be pretty much in place. The moon will be moving. Third, what the relative shape and size of the moon is. Basically, what you use there is 1/4 will be a crescent moon, 1/2 will be a half moon, 3/4 will be a gibbous moon. We'll talk about what these mean later, and 1 will be a full moon. And you put it, if it's a very thin crescent, it'll be less than 1/4. So a thick crescent will be between 1/4 and a half. A half will be a half. A thin gibbous will be between 1/2 and 3/4. A thick gibbous will be between 3/4 and 1. Okay? So you get your best guess there. And here is height. Oops, I'm on the wrong page. There we go. And here is Katie. I know you're in here. There you are. Oh, I already marked you. Okay. Does someone need a lab? Who's that? She's already left. Huh? Everybody does have a copy of it. Now, if you weren't here to hear the explanation, please listen to the video. Okay. Now, that's going to be the biggest time consumption of the lab, but it's only 3 questions. Okay. Now, all right. Now let's move to the part of the lab we're going to do in here. And this is a little bizarre, the way they put it together, but we'll do it. Okay. Part B, lunar phase nomenclature. We're going to do all this in the lab right now. People listening will be able to do it at home listening to it. They've mentioned several things. What is the new moon? When you look at the moon and don't see a bit of light. Maybe you can't even find the moon. Okay? This is a very thin part that's lighted. That's called a crescent moon. By the way, the spelling is C-R-E-S-C-E-N-T. It's there on your page 382. When, as the month wears on, when you see almost exactly half of a moon, you'll call that a half moon. It could be, if it came after a crescent moon, the first quarter. If it came after a full moon, before it's a new moon again, it would be a last quarter, okay, or third quarter moon. Okay. When you see more than half of the moon lit, that's called a gibbous moon. Less than half a moon is a crescent. More than half a moon is a gibbous. Okay? Gibbous is G-I-B-B-O-U-S. And then when you see all the moon lit, that's going to be full moon. Okay. Now, when night after night, more and more of the moon is being lit, whether it's crescent or gibbous, night after night, more is being lit. That's called a waxing, a crescent waxing or a gibbous waxing. Okay? If it's getting less night after night, that is a waning moon, a gibbous waning or a crescent waning. Okay? So those are the terms we're going to be using. Now let's turn to page 383. We're going to start in the middle of the page there. They've drawn it for you. They've drawn the sunlight rays coming in. This time the sun's from the right. Remember in the text I said the figure we were looking at, the sun was on the left. This time it's on the right. They've drawn the earth correctly. They drew a vertical line down the center of the earth, and then the right side, uncolored, they colored in the dark side. The white side is the side facing the sun. The dark side is the side outside the sun. So what you do, okay, and I'm going to try to do it here, okay, I'm going to try to get my pen set up. Okay, this is the earth. This is the sunlight coming in from here, okay. They've already done the earth. They did a vertical line through the earth and darkened the backside, okay. Then they drew moons around the earth. 1, 2, 3, 4, 5, 6, 7, and 8. Not very uniform. Theirs are much better. What you do with these, okay, draw a vertical line smack dab through each one of those, cutting it in half, right? This is middle of page 383, a vertical line cutting them in half, and you color in the left-hand side of every one of those. Okay, you can do a better job than I do, but don't do the side toward the sunlight, do the side away from the sunlight, and color in exactly half of the moon, the half that's away from the sun, right? Now, that's the first part of your lab. That's pretty easy, huh? Now the next part is to take what you're seeing there and filling it in at the bottom of the page. And the bottom, and they numbered these 1, 2, 3, 4, 5, 6, 7, and 8. I feel like a aerobic dance instructor. No, I don't. Okay, not really. Okay. Now, and I'm not really sure why they do east and west, except that's how they've kind of drawn it on the thing. But what they've drawn down here at the bottom are 8 moons there. 1, 2, 3, 4, 5, 6, 7, and 8. 1, 2, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, what you're to draw in here is you look from the earth at moon number 1, what do you see? You look from the earth at moon 1, what do you see? Second? Do you? You're looking from here. Yeah, you see only the dark side. That's all you see, right? So that's a new moon. So number one here, what do you see? Everything is dark. You see that completely dark moon, right? Okay? Now, from the earth here, you look up at the moon there, what do you see? Say again? You see mostly the dark side, but you're beginning to see a little sliver of light, aren't you?
Right.
Okay? So you indicate that sliver of light by drawing just a little arc there. Most of it's dark. Always the left-hand side is dark. You just got a little bit that's left light. Right? Okay? Look up at number 3, and what do you see? That rhymes. Every time. Huh? Half moon. You're absolutely right. So draw number 3 that looks just like number 3. Vertical line with the back side dark and the front side, the right side, the left side dark and the right side light. Don't draw anything on the white side. Look at number 4, and what do you see? Most of it is light. So this time draw your little sliver on the back side, on the left side, and just darken that in. Okay? Before you drew a sliver on the right side, but that's in the light. This time you draw the sliver on the dark side, and that you color in. Number 5, what do you see? Second? Full moon, don't draw a thing on there. You see it all lit. So leave it just completely illuminated like that. Number 6, look at that. What do you see? Again, most of it is light, but you see a sliver of it is dark. Okay? On the left, always. The dark is always on the left. Say again? I'm sorry, I can't hear. The dark is always on the left because the sunlight's on the right, isn't it? Here's the sun over here. Everything facing the sun is light. That's why it's good to use pencil on this. I should have told you that to begin with. Okay? Ink, you make mistakes, you got to draw you another moon and yours will be as ugly as mine. Oh, something. Okay. Look at number 7. What do you see? A half moon again, so draw your vertical line. And always the left-hand side is dark, the right is light. So it looks just like 7 above, pretty much. Look at number 8. What do you see? Okay. The right-hand side is just a little sliver that's light, and the left-hand side is all mostly dark. Mine are pretty ugly. Hopefully you can draw better than me. But you got the general idea of what's happening? Okay. Now we go to the top of the page. And here we're going to write down the names of the phases corresponding to our drawing at the bottom. Okay? What did y'all say that number 1 was? A new moon. That's all you put. New moon.
Number 5, 8.
No. Number 3 at the top of the page by number 1. You're looking at number 1 at the bottom of the page, and that's a new moon because it's completely dark. Okay? Now, most of the rest of these you're going to put down 2 things. The name of the phase and whether it's waxing or waning. Okay? So look at number 2, and what do you see? A waxing crescent or crescent waxing, whichever way you want to call it. A crescent waxing or a waxing crescent. Either way. Say again? W-A-X-I-N-G. Right. Like you wax your car or whatever you wax. Okay? All right. Number 3, what do you see? Half moon, or you could call it a first quarter moon because it's going from crescent to that. Either one you want to call it. Is it waxing or waning? Waxing because it's getting bigger night after night. Very good. Either a half moon waxing or a first quarter waxing. Either one will do. Look at number 4, and what do you see? A waxing gibbous or a gibbous waxing. G-I-B-B-O-U-S. Gibbous. Waxing or waning. Waxing. It's waxing, but either gibbous waxing or waxing gibbous. Either way. Look at number, okay, I'll let y'all finish writing. Look at number 5. What do you see? Full moon. It's neither waxing or waning because it's full. Okay? The night before it was waxing, the night after it's waning. But it's full moon that night, so that's all you put, full moon. Look at number 6, and what do you see? A what? A little louder? A waning gibbous, very good. Or gibbous waning, either one. Because it's more than halfway, so it's a waning, a gibbous, but it's getting smaller every night, meaning it's a waning. So a gibbous waning or waning gibbous, either one will work. Second, that's number 6. See, more than half of it's lit, that means it's gibbous, and because it went from full to 1 to half, that means it's waning, getting less every night. Okay? Look at number 7, and what do you see? Another half moon or a last quarter moon. How about what's it doing? Waning again. Okay. So either a waning half moon waning, a third quarter moon waning, or last quarter moon waning, or a waning last quarter. Yeah, there's several ways you can write it. Okay? Look at number 8, and what do you see? It's a crescent. Not much of one, but it's a crescent. And what's it doing? It's waning also, because in another night or two, it's going to be new again. All right? It's a crescent waning or waning crescent, whichever you want to call it. Crescent is Crescent. Crescent. All right. How we do it? Turn to the last page, page 384. Okay? This time it's asking at what time of day do you expect to see the full moon rise? Okay, where is the full moon? You're going to be my son again, right? Okay. Where is the full moon when it's a full moon? Back this way, behind you. So when is it going? Here's the key. It's opposite the sun. So when do you expect to see the full moon rise? When the sun is setting. Exactly, it's opposite that. So it'd be right around either 6 p.m. if you want to put a time on it, or sunset. Either one of those would do. Unless you, boy, I don't like people who sneeze too loud. I'm just kidding. I'm just kidding. You weren't here to hear my sneeze, were you? Okay.
Yeah, I was.
Okay, you were. Okay. All right. All right. Good deal. Now, when would you expect to see a new moon rise? Now again, where is the new moon? It's on the same side of the sun. So when will the new moon rise? In the morning, when the sun rises. Okay. So that would be about 6 a.m. or at sunrise, whichever you want to say. Is making sense? Okay. Yes, hey. Excuse me. I'm going to have to pause my recording for a moment here and hope that Jacob doesn't destroy mine. All right, let's go it again. When would a first quarter moon rise? Noon, right around noon. Okay, they missed all my indecision there. 12 noon. 12 noon. When would you expect a third quarter moon to rise? Midnight. You're absolutely right, because if the Earth's turning this way, which it is, then it would be coming up, and the third quarter moon is here, you're here, it would be rising right around midnight. As far from the sun as possible. Okay? Or 12 midnight, whatever you want to say. When would you expect the first quarter moon to set? Say again? I can't hear. Okay, if it rose at noon, it would be be setting at
Midnight.
midnight, exactly. 6 hours later. I mean, 12 hours later, midnight.
You have the third quarter, you talking about third quarter moon?
No, this is E is first quarter moon. Okay, did you get D? Okay, where are you?
Where,
Okay,
hold up.
we have 5, A, B, C, D, E, and F.
We don't eat.
Okay. And so, you are the same?
Okay, which was that? Yeah, D and E, because they're one's rising, one's setting, but they're opposite sides, yeah, they would be the same. Okay? And how about F? The new moon or a very thin crescent moon to set. Sunset, because the new moon is right with the sun. Okay? Y'all are good at this. Second? Right around sunset or 6 p.m. Whichever you want to put. Want to put a time for 6 p.m. around sunset. It rises at sunset because it's opposite where the it would be right with the sun. Okay. Now, you have just done the vast majority of the lab, but you've only taken a small fraction of the time for the lab. Okay.
Thank you.
Sorry. Now, so starting tonight, if it's nice outside, at least go out, pick your spot, pick your time, and pick your landmarks. Okay? If you don't see the moon, that's okay. Then go out every night after that until you can see the moon at that time, at that spot. Once you see the moon that first time, then try to do every other day that you can get out there and do it. If you can't do it every other day, then do the next day, and then the next day. But then once you see it again, then do every other day. If you can't do it that day, do the next day, or next time you see it, then do every other day. So once you've seen it, skip a day. If you don't see it, do it the next day.
So, see it, skip it out.
If you see it, skip a day and do it the next good day that you can do it. And then skip a day and do it the next good day you can do it. And then, once you finish the lab, turn it in. Your vast majority finished now, but you got to answer those 3 questions. It's going to take about 2 weeks. It may be a little longer if you don't see the moon for several days. It can't be any shorter than 2 weeks. Okay. It may be longer because you may see the moon for a few days and it disappears for 2 weeks and you see it for another few days. So that could happen. All right.
I see it.
All right.
Oh, you got it? Are you in a good mood?
No, we got nothing.
Okay. But if you see it through your bedroom window one night, that doesn't guarantee at that time you'll see it from that window the next time.
Okay, so skip it.
No. What you have to do is get somewhere where you have a bigger view than that.
That's what
Okay, I make that in the garage.
Yeah, you gotta go outside. You have to live in a bubble if you do it inside, you know. All right. I hope you don't think I'm cheating you out of your tuition dollars by letting